Okay, thanks a lot. Thanks a lot, Flavan. It means a lot for us. We are always in the constant endeavor to reach out to maximum number of people who are, trying to learn OpenFOAM, not only OpenFOAM, any other software that comes under the umbrella of FOSSEE. So the most popular software is Python. So you can all go back after this workshop, after learning OpenFOAM or simultaneously while learning OpenFOAM. I recommend to learn Python, R, and even Scilab also will be very much useful for you. And for chemical engineering students, please learn DWSIM, OpenModelica. These are all very useful softwares that are being used in the industry as well as in the academics. So if you're trying to go for higher studies, academics, as well as if you're trying to get into a job in the corporate sector, all this software will be very, very useful for you. Okay, we have 109 participants. I think we can start now. So Deepak, you can start the recording and we can go live on YouTube also.
You can start.
Okay, so a very good morning, everybody. I am Payal Mukherjee once again from FOSSEE IT Bombay. I'm working as a senior project manager here, as most of you know. And I have my team members with me, Mr. Paris Palkar and Mr. Evan, who will be demonstrating the hands-on sessions today after the lecture. Yes, good morning. Good morning, everybody. So let me first welcome today Mr. Nikhil Bhamare. Mr. Nikhil Bhamare is a founder at CFD Baba Simulations Private Limited, and he is also an esteemed member of the advisory board of the CFD team of FOSSEE. So let me just introduce him and then we can go ahead with the lecture session by Mr. Nikhil. So Mr. Nikhil has a bachelor's in mechanical engineering and master's in thermal engineering. He has been introduced to CFD during his master's. He had to spend a lot of time gathering the information that is spread across various resources to perform successful CFD analysis. He now wishes to help beginners in starting their CFD journey smoothly. Mr. Nikhil has solved various academic and industrial problems from all over the globe related to internal flows, external aerodynamics, heat transfer, porous medium, species transport, and multi-phase flows. He has the experience of training more than 4,000 students worldwide. He wishes to spread as much CFD application knowledge as possible to help new CFD enthusiasts to start their career with a sound knowledge of CFD. So over to you, Mr. Nikhil. Welcome once again, and you can start the session now.
Yes, thanks a lot, Payal ma'am, for the introduction, and a very good morning to everyone. I hope my voice is audible and clear
Yes.
to all.
Your voice is audible. You can also use the video and you can.
Yes, actually, I
Press.
just wanted to tell that I want to apologize. I am using a desktop for this streaming. That's why
Okay.
I won't be able to turn on
Yes, yes.
camera
I mean,
today.
sometimes the background is.
Yeah.
Yeah,
However,
I understand.
yeah, however, I just look like the photo which was posted for this webinar. So I'll just share my screen and I'll just
Yes, you can
start
share your screen.
with
Start the
the,
session. Thank you.
yes. Okay. I have started sharing my screen and I hope it is visible now.
Yes, sir.
Okay. So today we are going to look at this topic, key skills for CAD and meshing in industrial applications for CFD using OpenFOAM. So what will be the flow of discussion today? So I have 1 hour and I'll try to finish by 11:40 so that we can have some interactions if you have any queries. So I'll start with my first OpenFOAM problem and then what skills do students require, or even freshly graduated people require for industry? And then we'll look at a live industrial case study today. I'm not going to bore you with PPT. And then we'll look at what after learning skills. And then we'll close the session with some conclusion. So first point is the first open form problem which I solved in industry. So I started using OpenFOAM 8 years back for solving one industrial problem directly. So my first CFD tool was OpenFOAM, which was used for industrial application. And at that time, I struggled a lot to get the simulation done because industrial simulations are complex due to many phenomenons occurring together inside the CAD model or our CFD domain. So after I successfully completed that problem, I started this channel named CFD Baba, and I started it on YouTube first, and slowly it started growing. And now it has grown such that it is almost rank 15th in the entire globe of people who promote CFD. So it is now ranking with many top global open form promoters, and I have more interest to promote open form in India because CFD is done a lot in India, and if we can use OpenFOAM, then it would be a huge benefit to the cost required to run CFD simulations. And as you can see, this list was posted by Simon Fisher on LinkedIn, and he showcases all the people who talk about CFD. So in my last industrial visit at IIT Bombay, I had shown these things. However, this time we have a lot of new participants. That's why I am reiterating some of the things which were achieved. And they call it influencers, people who talk about CFD with passion. And this is the latest list. So now, after 8 years of industrial experience, I have started CFD Baba Simulations Private Limited, which is a CFD training, consulting, and software development firm. And our mission is to empower CFD users worldwide with CFD mastery. But why do we want to do this? Because many of you might have ran CFD simulations, and you know if you give wrong input, you will always get wrong output. So if you don't know what input you are giving, then it will create lot of wrong outputs, and that will be just wastage of time and energy. So that's why CFD users should at least know what they are doing, and that will reduce the trial and error a lot, which can give a huge benefit in the time and cost required for CFD simulations. And we do that through providing custom CFD tools, technical support, training, consulting, and also innovation. And the vision is a future where CFD is affordable, powerful, and accessible to all, starting from startups to also space agencies. Because right now CFD is expensive and it cannot be accessed by all very easily. So to fulfill this vision, till now we have delivered 200 projects and trained more than 5,000 engineers across 15 different countries. And I am also advisory board member at FOSSI, IIT Bombay. And FOSSI also awarded me the Mentor of the Year award, for which I am very thankful in recognition of the mentorship that was provided. And now let's look at the first industrial problem which I faced in OpenFOAM, which I was talking about. So for industrial simulations, you always need to simulate many models together. Like in this case, first there was a fan boundary condition, then there was heat generation, then there was rotation of the coupling, there was porous medium due to heat exchanger, and there were also porous medium at the bottom for openings. So many models need to be simulated together in order to simulate a real industrial CFD problem. So this was the thermal housekeeping of a wind turbine nacelle. So you guys have seen windmills, and these windmills have three blades at the front, and behind those blades there is this room-like structure. So in this room, when the blades rotate, the shaft also rotates. It passes energy to gearbox. Then the energy is transferred through coupling to the generator, and finally the electricity is passed down through the tower on which this nacelle is standing. So there are wires to pass down the electricity, and then it is collected at the bottom. So this is how a wind turbine works. And I had to simulate the heating of these components. And the problem was that this coupling was getting heated up above the above the reference temperature or recommended temperature. So the system in wind turbine is such that if a component overheats, it reduces the speed automatically of the wind turbine to cool that component, and that reduces the energy output. So we wanted to design a system such that the cooling of this coupling should be efficient. So there were 4 fans, 2 at inlet at the behind the nacelle and 2 at the top. So this was the mesh generated using Snappy Hex Mesh. And you can see how we improved the design. So in original design, you can see that the duct of fan 4 and fan 3 is not extended down. And now it is extended down, and it helps to suck in the hot air coming up from the fluid coupling. So this is the design modification suggested, which worked to reduce the temperature of fluid coupling successfully below the recommended value. So all this took me a lot of time and effort to complete, because 8 years back there was no tutorials and very less knowledge about OpenFOAM CFD on internet. So that's why I started myself to contribute to the knowledge of CFD on internet. So this brings us to you. What skills do you need if you are seriously trying to pursue your passion in CFD industry? So you need a combination of many skills together. So we have technical skills, we have domain knowledge, and we have practical and soft skills. So in technical skills, you need to have the knowledge of the tool which you are using. So the CFD tool can be anything. It can be any software, but you need to have hands-on practice with the tool. You need to be able to clean the CAD model, mesh it properly, set up right boundary conditions, and monitor convergence. Next, you need domain knowledge. That means you need the theory knowledge So for that, you need to read books on thermodynamics, fluid mechanics. And finally, you need practical and soft skills. So practical skills means that you need to have some uh, skills that can automate your work, which can be using Python to automate your work. And you also need to have good soft skills to be able to present the report to your customer. Because in the end, you just don't send the files to the customer and say that have a look. Most of the times, the people who are going to read your report are not CFD people, and they don't understand CFD. So you need to have soft skills such that you can make a common man understand your CFD results. So today we are going to look at live industrial case study of a data center, which is a rapidly growing infrastructure in many parts of the world. So this is what a data center looks like. There are many buildings, and inside the buildings, there are rows and rows of server racks. So these are just computers, and they are processing the data which is sent to these data centers. But during all this, lot of energy is consumed for running this infrastructure. And almost 40 to 60% of that energy is used in cooling of this data center. So since it is continuously running, it generates heat, and it releases heat into this room, and that heat should be removed successfully in order to keep this data center room cool. And that's why there are different mechanisms to remove heat from the room. But all those mechanisms require 40 to 60% of the total power to just keep this room cool. And why do we want to keep it cool? If it overheats, it catches fire and starts burning, and then the fire may spread and burn down the entire facility. So we want to avoid fire at any cost, and for that we need to keep the temperatures down. So for that, one of the concepts is hot and cold aisle concept, where we have server racks facing uh, so the front end is facing together and the rear end is facing together. So the from the front end of the server rack, cold air is supplied into the room, and it is sucked out by the CRAC unit, which is computerized room air conditioner, which can control the temperature and flow rate of air in the room. So basically what it does, it takes in the hot air, and then it sends out cool air from the bottom, and then that cool air comes out from these grills in front of the front end of server racks. Then the cool air gets sucked in, it transfers the heat with the server rack, and then the hot air goes out from this pipe back into the CRAC unit, and then again cool air comes out from the bottom, and this continues. So this helps us to keep the zone in front of the server rack cool, and the zone behind the server rack is hot region. That's why it is called hot and cold aisle concept. And the benefits of doing CFD is that, as you know, we have total 40 to 60% power used in this. So that means huge cost, almost 40-50% cost goes in designing the cooling system of this data center. So in that, CFD plays a very crucial role because it can predict the hot and cold regions even before we build the real data center by investing millions of dollars. So that's why if you are even able to optimize the percentage of cooling by 5 to 10%, then it would result in thousands of dollars saved for each data center. So that's why this is important to study. And let's now start with the case study. So I have this step file of CAD model ready with me. So I'll be simulating this in OpenFOAM. However, I'll be using this tool, Bind Simple Foam, CFD Forge V2412. I'll just open it. And here we have the GUI of Bind Simple Foam CFD Forge. So you can set OpenFOAM path here, and I'm using OpenFOAM version 2506, but you can use any ESI version using CFD Forge. And you can set the paraview path. So currently I'm using paraview 5.13. So you can use any path. And now we need to select the working directory. So I'll use this same working directory, this PCD IITB industrial case study, copy it, and I'll just paste the path here. And this folder is selected, and I'll select the folder. It says, do you want to create new case? Say yes. And now the template case is extracted at the location. So now you can see we have 0 constant system folder, which are required for OpenFOAM simulation. And now we need to bring in the CAD model. So this is just a small demo how we can use this tool CFD Forge. So for this, I will use a dummy CAD model first. So I'll go in the resource files, which is already provided, and I'll go to demo CAD models, and let's use the multiple outlet pipe. And I can select all the STL files. So it supports STL files, and you just need to name the boundaries, click on open, and it has imported and combined the STL files. So let's analyze the geometry to view the dimensions in X, Y, and Z direction. So the pipe is 1 meters long, 0.2 meters in Y, and 0.95 in Z. So it is quite a big pipe. And we can click on View CAD, and it will open the CAD model in ParaView software, which is again open source tool for post-processing the simulation results. So I can hide in the boundary STL, and I can only turn on CAD.stl. And you can see this is the geometry. We have this inlet face, we have the walls, and we have the outlet. So we have 4 outlets. And now we need to mesh this model. So to mesh it, I can simply enter the minimum cell size, maximum cell size, and a number of layers, and the number of processors I want to use. So let's try to mesh with default settings and see what we get. And then we'll modify the mesh as required. So I clicked on save mesh settings and generate mesh. And it generated a mesh with 25,000 cells, and max QNS is 2.89. So recommended is below 4. So the mesh quality is fine, but we cannot just trust the quality. So we will click on view mesh, click on apply, and we need to visually inspect the mesh. So you can see here that it has created 3 boundary layers, but the mesh is very coarse here because at the outlet only 3 or 4 cells are created, but we need more cells. So let's decrease the minimum cell size to 0.05, which is 5 mm, and again save the mesh settings and generate the mesh. So it is using Snappy Hex Mesh to mesh this CAD model. And again, the mesh is done, but this time cell count is 68,000. It has increased almost 3 times. And max cueness is below 4. So to just view the new mesh, simply click on the refresh here and click on last frame button. And now you can see that the mesh is refined and created properly at the outlets. We can view the cut section by taking a plane normal to Y and viewing the cut section. To look at the boundary layers, so 3 boundary layers have been created properly across the domain up to the outlet. Now we need to solve this simulation. For that, we need to define the material properties. So the default properties are set for air, and we need to enter the gravity direction, which is negative y in this case. And then we need to specify inlet velocity, direction, pressure at outlet, temperature at inlet, K and epsilon values, and turbulence model. So let's set the inlet velocity to say 10 meters per second, but I need to view the direction of inlet. So the flow will go in negative z direction. So I will set it in negative z as minus 10 meters per second. And for inlet temperature, let's keep 300. And K and epsilon values can be calculated by using the formulas for K and epsilon. So it is provided in the resource files folder, this turbulent calculator Excel. And you can calculate the value of K and epsilon by providing the hydraulic diameter, speed of fluid, and the turbulent intensity. So I have already calculated it. So for 10 meters per second flow and hydraulic diameter 0.1, I have to use this K and epsilon value. So I'll simply copy paste the values for K and epsilon. And I'll set the model to K epsilon turbulence model. And just click on Save Setup. We can close the Excel. And now I'll go to solve, and I need to solve. So I'll enter 1000 iterations with right interval of 100 iterations. So after every 100 iterations, it will write the results. And if you go to monitor plots, you can visualize the residuals, how your solution is converging for velocity, pressure, energy, K and epsilon. And once 100 iterations are completed, it will write a data folder of 100. So we can view the results while the simulation is running. Go to post process and click on view results. And it will open ParaView with the results loaded for the time steps that are solved. So here we can see pressure. We can view the cut section again to view flow inside the pipe. We can see this is the static pressure. We can view velocity, which is 10 meters per second coming in at inlet, getting spread across inlet and outlets. We can view temperature. It is almost same, 300 to 300.1. Then we can view Y plus, which is the maximum Y plus is 156, and we are using K epsilon model. So Y plus should be between 30 and 300. So we are using correct Y plus values with the help of our boundary layers. We can also inspect the total pressure and the static pressure. And here in the monitor plots, we also have pressure monitor, which tells us the value of pressure at inlet. So if this plot becomes stable, that means our solution has become steady state. So these are all the things you can do with CFD Forge. However, this tool is not built for toy CAD models. So now we will simulate a real industrial case of full scale data center. So I can abort this simulation and it will stop. So it has run up to 800 iterations just on a single core. And I can use this option, clear time folders, and it will clear all the time folders. And now I can start with my new CAD model. So let's import another CAD model. And this time I have this folder named CAD where I have the STL files. But I don't have them right now because we will prepare them using FreeCAD. So I have this FreeCAD open. I'll open parametric part. And now I need to import my step file. So this is the step for CAD preparation. And I can go to file, import, and I can paste my path and double click on step file, click on OK to import my step file. And here you can see that I have my step file, which is a single solid. I mean, it is a fluid domain of the air extracted inside the data center. So how to view it? Right click and go to toggle transparency, and you can view inside the CAD model. So this is a full scale CAD model. And we have many server racks here, and we have two CRAC units on the left, and this is a raised floor data center. That means cold air will come in from the bottom, which is a false basement kind of height, and then hot air will escape from this false ceiling back into the CRAC, and then again from the bottom of CRAC cold air will come in, and then again it will come out through these grills provided at the floor bottom. It will carry heat from the data center racks. It will go up through these openings provided at the top. Then it will go here, and then it will again go back into the CRAC from the top. So this is how the circulation of the air is going to be. And we need our STL files to run this in CFD Forge. So how can we do that? For that, we have this option. We can go to part, workbench. We can select top air, and we can go to part. And here we have this option to make the compound explode. So I'll go to compound, explode compound, but you can see it has just created one single. So I'll again select it and again go to part, compound, and explode compound. And now you can see it has created each face separately for our CAD model. So now we just need to name our boundaries. So I'll name inlets and outlets. So I can select any face and press space to hide it. And this way I can hide the ceiling. And now we can see inside the room. So here we have the CRAC inlets. So I'll select this face. I'll press Control on my keyboard and I'll select the other inlet face. So both are selected. And we'll use this tool union to make them into a single part. And we will name them as CRAC. These are actually outlets because air will get sucked in from the top. So I have named it as CRAC outlet. Next, we will name CRAC inlets at the bottom. So I'll hide this floor. And here we have the inlet face. So I'll select this face, press Control, select another face, use the union tool and name it as CRAC inlet. I'll hide these, which we have already named. And now we need to name our server rack inlets and outlets. So I can hide the walls, and here you will be able to see our server racks. And this is the inlet face of the server rack. Air will come in from these bottom openings, and then cold air will come in from bottom and get sucked into this face, and then it will heat transfer through the rack and it will come out through the back face of the rack. So this will be our hot air inlet into the room, and this will be our cold air outlet out of the room through the server rack face. So let's name them accordingly. So here we need to name the faces of hot server rack. So I'll select the faces, 4 faces, by pressing Control on my keyboard. I have selected all 4 faces. Make them union, press yes, and we can rename it by simply pressing F2, and we will name it as hot air inlet for what? Rack. So I have named it as rack hot air inlet into the room. And finally, we need to specify the hot cold air outlet. So from where will the air get sucked into the rack? From these faces, which are in front of the grills at the bottom. So I have selected these faces, make them union. Yes. And I know it might be fast, but you can watch the recording, which will be provided. But right now, you at least are getting to understand what we are doing and what is the actual process you need to do in industry. So we have named the rack cold air outlets as well. And cold air will escape from our domain through these faces. So I'll hide these. And now whatever is remaining is nothing but our remaining walls. So I can do one thing. I can hide the exploded part and again show it. So it will show all the faces. Then I'll just hide the ones we have named. And now whatever is remaining are the walls. So we can select everything else and we can combine it using union tool, and we can name it as walls. So we have named our patches walls, inlet, outlet, and now we are ready to export the STL files. So I have this macro to export STL, and I can simply select the location. So I'll export my STL here in the STL folder, and I'll paste the location, and it will select this folder. And if I view the Python console, it will show me that the CADs were exported, and we can check them here. So you can see it has exported all the CADs, and it has also combined it into a single CAD named CAD. Now we are ready to use CFD Forge. We have our STL files. So we just need to select the boundary faces, not the combined CAD model. Click on open. It has imported 5 STLs. Analyze the CAD. So it is a full scale model. The length is 10 meters, width is 6 meters, height is 4.37 meters. And we can view our STL files in ParaView now. Click on apply. Hide all the boundaries and just turn on cat.stl. We can make it solid color and we can reduce the opacity to view inside and just inspect that everything is fine. I can see that everything is imported correctly from FreeCAD into STL. And now we are ready to do our mesh. So this is a very big problem. And we need to be careful about mesh size. We can't create a very fine mesh. So I am going to showcase with coarse mesh due to time constraint, and also The objective is not to simulate accurate simulation, but rather to show the procedure behind simulating it. So we can enter a minimum size of 50 mm and max cell size of 100 mm. So why am I choosing this? So this is the meshing strategy. So here I can see I have this small face here, which is the smallest face in my geometry. So I need to measure its dimensions. And if I try to measure it here, how can I do it? I can use this create ruler option. I can click on a point here and I can again press P on my keyboard to create another point. Click on apply and it will show you the height, but it is not showing it accurately right now because I did not click using the normal view. It is something else only. So for that, you need to measure it in a normal view. You can go to camera parallel projection. You can set the view and you can see it was measuring something else entirely. So let's select correct height. So press P here, point the mouse, press P. Again, press P on the surface. You can adjust it. Click on apply. So it is 0.1 meters, which is 100 mm. So we need at least 2 cells across the smallest face. That's why I am using 50 mm for the minimum cell size. Now let's look at the maximum cell size, why I am using 0.1, which is 100 mm. So let's see the dimension of the room in the longest length, which is the ZX direction. It is 10.5 meters. So I need at least 100 cells across the length. So if I divide this by 100, so this is 10 meters and it will be uh, basically 100 mm if I want 100 elements along the length of 10 meters. So I'm using max cell size 0.1. And now I need to select location in mesh. So it can be any point inside the mesh. How do you create it? So I'll delete ruler. Press Ctrl and space on your keyboard to open the filter. Search for point source. Double click on it and it will create a point in randomly in the domain. So now we need to place it such that it will be inside the fluid domain. So this is where my fluid domain is going to be. Air is going to flow in from this server bottom, I mean CRAC bottom. Then it will flow through the bottom of the room, come out through these grills, and then it will go up, and then it will escape through the outlet grills. Then it will again be sucked in back into the CRAC units. So this is the fluid domain and my point is right in the middle of the fluid. So it can be any point anywhere. So I can just copy paste the coordinates or enter them. So this is minus 0.01. It is fine. Then next is minus 0.268 and it is 1.11. And I'll use zero number of layers because of time constraint, but we can add layers like I displayed in the multiple pipe outlet. And I'll use 4 cores to make it fast. So I'll save the mesh settings and generate the mesh. Let's see how it generates the mesh for such a big CAD model in such less time. So it has now created 4 processor folders and it has decomposed the mesh. Now it is creating a snappy hex mesh. Now it is reconstructing the mesh. It has finished meshing. And it has created 470K cells with a max skewness of 3.74, which is below 4. So this quality is acceptable, but we always need to inspect the mesh visually to be sure. So let's view mesh. Click on apply. And we will turn on surface with edges to view the mesh. And this is the snappy hex mesh. And you can see that it has captured everything. Let's look at those grills. So yes, at the grills, we can see it has exactly created 2 cells like expected, because the total length was 100 mm and we gave minimum size as 50 mm. So it automatically detected the smallest faces and applied 50 mm there. We can we can also view the cut section by taking a cut section, let's say along Y. You can turn off triangulate slice to view the mesh without the crisscross triangles. This is the actual cut section. And you can see the smart automated workflow of CFD Forge has refined the mesh where it is necessary. Like in this case, the air was going to flow out from here, so velocity is going to increase here. So we need some refined mesh in order to capture that velocity increase accurately. Same thing at the bottom, from where the cold air will come into the room. So our mesh is created and now we can solve it. So I'll use the default properties of air. I need to select the direction of gravity. So gravity always acts in downward direction, which is negative z. So I will enter the direction of gravity in negative z direction, minus 9.81. We can use the inlet velocity as any value. So let's use 100 because we will change it later. Outlet pressure will be atmospheric pressure. Let's use room temperature of 300 Kelvin, which is 27 degrees Celsius. And we can change back K and epsilon to their default values of 0.1. And we'll select turbulence model as K epsilon for this case as well. Click on save setup and the setup is saved. But before we click solve, we need to change the boundary conditions of inlet. So how can we do that? We can go to resource files, and here you see we have this inlet boundary condition file. So we can open it, and to change the boundary condition of our inlet, we can go to 0 folder U file and open it. And now you can see we have our CRAC inlet and rack hot air inlet, for which we want to change the boundary condition. So we want to specify flow rate, volumetric flow rate on those faces. That's why I will copy this boundary condition, flow rate inlet velocity. And I'll replace the boundary condition of CRAC inlet and rack hot air inlet. So I'll use a flow rate of 8.9 for CRAC inlet, and for rack hot air inlet, the hot air will come into the room at 3.4 meter cube per second. Next, we want to change the temperature. So at CRAC inlet, cold air comes into the room at let's say 20 degrees Celsius or 15 degrees Celsius. So we can either use 288 or 293. So for this case, I am using 20 degrees Celsius coming out from CRAC. And CRAC outlet, we will keep initially at room temperature, which is 300. And then rack cold air outlet, we want it to be initialized with the cold air temperature, which is 293. And rack hot air inlet, so the hot air coming in from the rack faces, let's assume it 40 degrees Celsius. So how much will it be? 313 Kelvin, right? And we will save this temperature file. And now we are ready to run the simulation. So I can go to solve and let's write the data interval at 20 every 20 iterations. Let's solve just for 500 just to visualize the initial flow, and I'll click on solve. But before solving, I need to change something in the control dict file. So I can press abort here and it will abort the case. So the thing is, in system folder, we have control dict, and here we have specified to measure inlet at, pressure at inlet and outlet patch. But since we have multiple patch right now for inlet and outlet, we don't need it. I'll delete it. And it will take time to write those values. That's why, due to time constraint, I have deleted it. And now we can clear our time step folders again, and we can try to click on solve, and it should start the decomposition of the case. So it has created 4 processor folders, and then it will start the iterations and we can monitor them in the residual plot. So it has started and it will write the data after every 20 iterations. However, this is in parallel. So it will write the 20 folder inside the processor folder. But we can view the results while case is running. For that, I will close all the other paraviews and go to post process view results. So how to view results for such big case, because we cannot just show one plane, right? It would not explain anything. So that is the next skill you need for post processing and making the common people understand. So I'll reduce the opacity and I'll create some planes to visualize the results. So let's create the first plane, and we'll create it such that it cuts the CRAC.
Hello.
Yes, ma'am.
Is the video stuck or I was
Yes,
thinking there is some
the video.
technical glitch from my side?
Let us wait.
I think he's got disconnected. He'll join back.
Uh-huh. Yes,
Yeah.
let us wait. Yeah.
Yes, ma'am.
If you have any queries, you can write down in the chat box. Then we will, after this talk session, we can take it up one by one.
Okay, so far, whatever Mr. Nikhil is explaining, are you able to understand? You can put a thumbs up in the chat, or you can just unmute and say yes, no. Okay. Because Mr. Nikhil is purely from a heat transfer background, so he has those applications like cooling and all of those. What strategy to use to cool the data centers and how to decide? Okay. Okay, so see that in data centers, at least having a liquid cooling is a bit more difficult because you have electronics, right? So those fluids and all, which are deionized and all of those, so they become a bit expensive. So that's why larger data centers prefer air cooled rather than liquid cooling. But if you want to simulate that, and you can do that, like you can take it up as a case study, and you can see the difference between a liquid cooling and the air cooling, and you can see whether the scalability is feasible or not. So that is one way you can do. You can then compare the data also, what you're getting, which one will be better. Obviously the liquid cooling will be better, but when it comes to scaling up, it will become a bit difficult. So in that sense, you can try to differentiate between both. Okay, what is CFD Forge 2412? So CFD Forge is something like a front end, you can say. In like now continuously in the previous workshops, you've seen that we were every time typing everything in our terminal. So the Forge part is like a GUI, you can say, in which like as Mr. Nikhil was demonstrating, he just added in the values he wanted. He just clicked a few buttons and he was able to make the whole mesh. Then he was able to complete the whole simulation and all. So it's just like a front end, you can say. Okay. Since it's air fluid model, so can we use this procedure for UAV and aircraft modeling? Now, in a UAV and aircraft modeling, you are typically solving Navier-Stokes equation only for your air. It's a single phase simulation. So for those,
Yes, sorry,
yes.
I'm back. Wi-Fi just decided to switch off for no reason.
Okay,
But yeah,
okay,
uh, I'll just share my screen again.
sure, sir.
So where were we? Could anyone tell me when I got disconnected?
Yes, so you were demonstrating the plane cut section.
Okay, so how many planes had we cut?
You were just starting off with the
Just
plane.
written. Yes.
Right.
Okay.
So I can delete all the slices I did, and you can simply select and press delete. So we have this case.form, and now we need to create the planes. So how can we do that? Use this plane option. And we cannot just create a single plane for this complex CAD model. We need multiple planes. So we need one plane at the center of CRAC and the inlet ducts at the bottom. Click on apply. You can see these partitions are due to the decomposed mesh which we created, but we can ignore them for now. And I'll create another plane at the center of second CRAC. Click on apply. I had to first select case.form and then create a new plane and then place it and press apply. I can hide the plane bounds. Next, I need to create a plane which will show us the velocity coming out uh, from the bottom in horizontal view. So I'll select Y and I'll just take a plane at the second grill location at the center. Click on apply. And finally, I'll need a plane to view the hot and cold regions. So I'll create a plane and make it horizontal. And let's view it at a height almost at the center. And we can hide case.form, and to view the results I had selected reconstructed case by default. However, we are running
Okay, so I think Mr. Nikhil is facing some technical issues. Let's wait for him. In the meantime, as I was saying for Mr. Vimal, so if you are just trying to simulate a UAV or an aircraft model, it's a single phase, so you don't need to necessarily uh, distinguish between the air and like your fluid properties in two different terms. You can keep the whole fluid domain as air only, and you can simulate for that. It will be much more simpler. Like if you want to calculate something more like some particles or something, then you can use a multi-phase model. That would make more sense. But if you're just going for a single phase simulation, just going with air is fine. And okay, so there is one more question of suppose we have limited space in a large heat. So how do we decide cooling method? And now, like you can take this in terms of laptops and all. You have a very limited space and you have a lot of heat generation under load. So in those cases, sometimes the liquid cooling may be feasible, but again, it comes down to the costing and scalability. So if you have the resources and you are able to fit in a liquid cooling, you can go with liquid cooling. Obviously, liquid cooling will be much better compared to air in specific terms. Okay. Most of the time you find that air is much better than liquid. So it's a bit of a controversy right now. So you can choose irrespective of which one you are going with. You can choose either air or you can choose what liquid. And depending on how much heat transfer you want to do, like in a specific amount of time, how much heat you want to transfer from that particular medium to the environment, that also matters. So that is where your liquid air will come into play. Is it possible to share this case study? When Mr. Nikhil will join, we could ask him that. Yes, FreeCAD is open, so can you recommend any tutorial for that? So for FreeCAD, if you're starting off with FreeCAD, there are multiple YouTube tutorials. You can just type FreeCAD tutorial beginner and you can go ahead on YouTube and learn that. It's not a big deal. We do have FreeCAD under the FOSSEE banner as well, and it's still in the preliminary stages. So we can, like in the future, you can expect some FreeCAD tutorial, like the spoken tutorial that we have for OpenFOAM. Okay. Can we use jet cooling? Uh, by jet cooling, what exactly do you mean? In what sense? Could you elaborate a bit? Okay. Mr. Mohammed, the attendance sheet will be shared later on. So whenever it is shared, it will be put in the chat itself. Okay, impinging cold air into the heat system. Now, if you want to do something like that, you if you want to simulate something, you can do that, obviously. You just have to change a few boundary conditions. Like if you have that inlet condition, like in Nikhil sir's case, you are giving some heat, you're giving some inlet from the bottom and you're taking an outlet from the top. So in that sense, you can just change the boundary conditions and you can implement that jet boundary condition. So there are multiple ways to do that. So you could try that as well. Okay. So once again, the meeting links that, not meeting links, but the recording links that we've shared, those will only be available and will be usable for a set time period. So download it like a month or so. So you can download those videos and keep them, because after some time that link will just get deactivated. So if you are planning to keep these videos for your reference in the future, obviously the videos will be available on YouTube in a few weeks. So you could download it from there or you could watch it over there as well. But if you want to download the current videos, you can download and keep it because that link will deactivate after some time. Okay. So for now, just let's wait for Mr. Nikhil. Okay. Okay. For the structured mesh, Paris and Manzil both have answered. Okay. Okay, so the liquid cooling question is continuously in the chat. So let's wait for Mr. Nikhil, and maybe he could answer that in detail. Since he is properly working in that background, he'll be able to differentiate better between liquid and air cooling and which liquids are better. Okay. Yeah.
Hello, sorry, there was a power cut at my end. I hope my audio is clear now.
Yes, sir.
Okay, so you guys have got an idea of how the entire process is. Only the results were remaining. However, I have joined from my laptop and I have the PPT with me. So I'll just continue and end my presentation in just 5 minutes. So I hope my screen is visible again.
Yes, sir.
Yes, sir.
Yes. So we just saw how to perform the simulation using CFD Forge for such kind of flow phenomenon, where cold air was rising up and hot air was going out through the CRAC. And the tool used was CFD Forge. So this tool was developed at CFD Baba Simulations Private Limited. And the motivation behind this tool was to simplify the open form workflows, especially for specific applications. And you saw that in 7 clicks, we went from CAD to results. And the features are that you can import STL files, you can mesh it, you can set up the boundary conditions, run the simulation, launch ParaView without any core or mesh count limit. So there is no limit for mesh count or number of cores you can use. You can use as many cores as your PC has. And it is built using or powered by OpenFOAM, and plus smart automation workflow. So why is it smart automation? Because you saw that we did not need to deal with any boundary condition names or any other settings. We just simply selected all the things necessary, like uh, mesh settings, material properties, boundary conditions, and we didn't need to worry about any other files. So it automatically takes care of all the other files. And it is a licensed tool, and it has expiry date. So this is a 1 year license right now, which I'm using. And all the rights are maintained by CFD Baba Simulations Private Limited. So next, uh, how can you get this tool? So anyone here who wants to try it can drop me an email at cfdbaba@gmail.com with subject CFD Forge Access, and you can get access to this tool on your own computer. You don't need to do anything extra. You just need to have OpenFOAM and ParaView on your system already installed. And even if you don't have it installed, I have a guide on how to install OpenFOAM ParaView from scratch. And then this CFD Forge is like another installer file. You simply need to install the setup by clicking next and then finish, and it will install CFD Forge in your system, and then you can access it with a license key. So what after learning these skills? So if you want to go in application side of CFD engineering, then you should have command on the tools that you are using. And if you want to go in the development side of CFD, then you need to have coding knowledge like C++, Fortran, and also Python can help for automation of tasks. And you should have a good portfolio in form of PPT and put your best complex problems. But before creating the portfolio, do at least 20 problems, different problems hands-on, and just put the best problems in the portfolio. And when to use it, the portfolio, if you go to job interview, you can ask permission to show a portfolio of CFD projects which you have done. And most of the times, if your interview is online, you can screen share the PPT presentation and present it. And try to make it domain expertise. That means whatever field you choose, try to learn the theory in deep behind all the applications in that field. Because in CFD, you cannot do multiple applications at a single time. Once you join a company, you will mostly work within a certain range of applications. So make it domain expertise. And you should have these basic understanding of things like turbulence models, porous mediums, heat transfer, heat sources, multi-phase flows, a little bit about combustion. If you know, that will help a lot. And you should have your LinkedIn updated and approach CFD professionals on LinkedIn. And how can you solve these 20 problems hands-on? You can model them from papers. So we have research papers, which is what will help you to get the CAD model boundary condition and replicate it to solve the CFD simulations. So you can learn more at our website, cfdbaba.com. And I have uploaded lots of learning resources on my website. I can quickly show it to you once. So right now I just copy pasted this. However, I can type in and it will show me the link. And you can search CFD Baba on Google, get this website. And here, if you go down and click on Learn CFD, you can see I have uploaded lots and lots of resources for learning OpenFOAM as well as other CFD tools. And if you go to the home page, we have also started industrial CFD training where you will get exposure to the live industrial projects which are performed in industries. So you can go to this page and check it out. It is there on the home page. And finally, I'm very thankful to Fossey. It is always special to speak here because IIT Bombay is where my CFD journey truly evolved when I collaborated with Fossey and open source community. So thankful to all Fossey members for this community. And I want to encourage and implement usage of OpenFOAM in Indian CFD industry. And that's why uh, I am sure that I can achieve this with help of Fossey, and I am always ready to offer all help and to collaborate with Fossey. And if you would like to contact me, I have this mail ID. You can note it down: cfdbaba@gmail.com, and follow me on YouTube, where I have almost 800K views now across the channel. You can connect with me on LinkedIn, where I have more than 16,000 followers, also on Facebook and Instagram. So, thank you for listening patiently. This is just an image of a lion which was simulated in OpenFOAM for external aerodynamics simulation, just to understand if the shape of lion is aerodynamic or not. And it turns out that the shape of lion is aerodynamic because the lift coefficient value was more than the drag coefficient value for flow over this lion. So that's all from my side. And now we can have a Q&A and I will be happy to answer all your queries.
So there are some questions in the chat.
Okay,
Is-
I will go through them. So this tutorial supports OpenFOAM or will work on ANSYS? Yes, it can work on any CFD tool. It is more about setting the correct boundary conditions and knowing the procedure, how to prepare your CAD model and how to mesh it to get required mesh to capture the flow phenomenon accurately. So I am taking questions and you can ask in the chat box if you have anything to ask, because I am not able to see earlier chat messages. I can only see one message. If you can read out the questions, that is also fine. I
Yes.
will answer.
So there was one. Okay, okay. Can I ask the question?
How much heat is generated in the data center that you have mentioned, or the wind turbine case?
Yes, yes, yes. So it was a volumetric heat source and heat was generating in that case. And that's why there was high temperature rise through the nacelle.
Are any values? How much heat was generated?
Yeah, as far as I remember, it was something around 120 watt, and that can be converted to watt per meter cube as per the volume of your heat source.
In the data center space?
Okay, in data centers, you are asking.
Both, sir. I'm asking both cases.
Yes.
How
So
much?
for data center, it is different. So from each rack, we were assuming around 1 to 2 kilowatt heat getting extracted. And accordingly, for this demonstration, I had simply set a hot temperature outlet at 40 degrees Celsius for the case. However, in reality, the rack can generate heat of 1 kilowatt up to 3 kilowatt based on the size of your server room.
So how much total heat was generated in the room? Sir?
Yeah, so we were not able to conclude that study because of power cut. However, I will try to post the results. I'll run that again, and I'll take snapshots or a video, and I'll try to post the results on social media on my LinkedIn. So please make sure to follow on LinkedIn. I'll post the results today as a summary of today's session. And there you can see all the temperature changes occurring. I'll also write a paragraph about this.
Okay, sir. And sir, you told that 2 to 3 kilowatt of heat was generated from a single server unit. So I'm
Mhm.
asking total server units that you were using in the
Yeah.
simulation. That would amount to like 10 kilowatt, maybe if five server rooms are there, server units are there.
Yes, so in our geometry, there were just 3 server units in one rack, and there were total 4 racks. So I think there were only 12 units. However, I had combined all the faces, inlet and outlet faces of the 3 units in one rack, and that's why it was a single face.
No, no, I'm asking how much heat was generated. Like for 2 kilowatt, if we are assuming for single, then for 12
Yes,
units is 24 kilowatt maybe, है ना?
yes. But in this case, like I said, it was not about the accuracy of the simulation. I just assumed 40 degrees Celsius coming out from the server room faces, rare faces, because that is what the temperature is generally, which comes out. It was a simplified case.
Okay.
Yes, and of course, the flow rate changes with respect to the heat load, and heat load also changes because the air is recirculating in the room. So that's why it is a fluctuating thing. And in reality, to simulate it, we need to enter the values in a table kind of format where we define how it is changing with respect to time or iterations, or if it is a function of temperature, that also can be defined.
Okay,
Right,
sir.
that all
And
is advanced methods. Yes.
how about, sir, going beyond simulation, if we have to decide for suppose 2 kilowatt, we have to give a cooling and we have to uh, check whether which fan or fan cooling is provided. So CFM and all, have you ever decided that rating and all, what CFM of fan can be used for this cooling?
Yeah. So the flow rate values which I used at the CRAC inlet and the uh, server rack outlets. So those were calculated from CFM, real CFM values, of course. But like I said, that was not the motivation behind creating this study. It was just to show the procedure from when you get to CAD until when you get the results, what all you need to do in between. So, all you are asking is the theory part, which can easily be found in many research papers. And also, there is a lot of experimental data where it tells you how the CFM changes with respect to the change in heat load of the server room racks, and they vary from geometry to geometry.
Okay, sir, I got it. And if assuming that temperature difference of 5 to 7 degrees there, and so for single degree of degrees, we have to provide different value of heat that we have to remove. Is it we have to multiply it for 7 times if say we have 7 degree Celsius difference?
No, uh, we don't need to multiply it. If we separately specify the phases of the hot and cold server air inlet outlet. But right now, as you see, due to time constraint, I had selected only the combined faces. So all the faces of server inlets were one patch, and all the faces of server outlet was another patch. So in reality, you can model them separately, and then you don't need to divide anything.
Okay, thank you, sir.
Yes, so another question, is it possible to share this case study? Yes, once you mail me for the access to CFD Forge, this case study will also be shared.
Okay. So there was one question previously. I think when you disconnected, it was there. So there was one participant asking whether liquid cooling, liquid cooling, how do you decide which liquid is best for cooling? And if you have a specific area constraint, how do you decide between air cooling and liquid cooling? So that was the question. So could you answer that?
Yes, liquid cooling is very expensive because it has lot of maintenance. So usually it can be used for small, medium scale projects, but for large scale projects, usually air is used because it is much cheaper and more proven way because it has been used from many years now. But liquid cooling is a relatively new concept, and leakage is the main problem in liquid cooling, and that requires a very high maintenance.
Yes, sir.
So it varies from application and budget of the project.
Yes, sir. But I think the question was more relevant towards if you want to simulate such a thing, what criteria would you satisfy for liquid cooling?
Okay, for simulation.
Yes.
So, first, the CAD model needs to be appropriately modeled as per the fluid domain. It should be watertight. And then you can assign different fluids. Suppose if you are using water or another coolant, you can define it. And if you are using air above it, then you can also define air as the another material. But once you define two materials, it becomes a conjugate heat transfer problem. So you cannot solve that kind of simulation in bind simple form. It is for a single material. So for multiple materials, you can use solver named CHT, multi-region simple form, for doing steady state simulations, or CHT multi-region form for doing transient simulations.
Okay, sir. Thank you, sir.
Sir, there was also one question that the forged run the scope of forged run is only limited to buoyant foam, or it can run multi-phase as well.
Yes, so CFD Forge is a custom tool which is developed for specific applications. So the tool which I demonstrated was bind simple form, which can be used for any CAD model to simulate flows which have buoyancy in them, like in this case which we saw today. So CAD model can be anything. We also simulated the flow through multiple outlet pipe using same solver. So CAD can be anything as long as the physics is incompressible flow with heat transfer, and turbulence is also considered. And similarly, I have different versions of CFD Forge, like I have CFD Forge Simple Foam, which you can use to solve external aerodynamic cases for subsonic flows, or you can even simulate internal flows using it for flows where we don't have heat transfer. So similarly, we have by CFD Forge Interfoam, which solves for multi-phase flows. So for each uh, application or for each solver, we have a different version of CFD Forge.
Okay, sir. Thank you, sir. Okay, so for people who are asking about HVAC systems and room cooling and all, we have a session in the afternoon. So that time we can take up those types of questions. So if you have any questions for Mr. Nikhil regarding the CAD generation or something related to his cases that he's just showed us, you can ask those. Okay. So if there are no more questions, we can go ahead with the demonstration session by Paris.
Actually, I have a question for Mr. Nikhil.
Okay.
So, yeah, Mr.
Yes,
Nikhil,
I will.
yes, this CFD Forge that you just talked about, this is a licensed software, you said. So people have to
Yes.
pay for it. Is it a payable thing or how is it?
Yes, it is a licensed software with 1 year license validity, and
Mhm.
currently it is available only for companies and industries. But soon
Okay.
it is going to be made available for students as academic license, and then they will be able to use it for a limited period of time for free. So
Okay. Okay.
yes, it is going to be provided for free
I was curious
once
about that
we
only.
yeah, the academic version always needs to be there. Otherwise, how will students access it? So, of
Yes,
course, I
yes,
have
yes.
thought about it. And yes, the people who mail me for CFD Forge access, I will send the link to access the software for a limited period of time for free.
How much
It
free
will be
time? 1 year, I think.
one
1 month.
month period.
Okay, okay.
Yes, 1 month would be enough to run many simulations because, as you saw, the tool is quite fast and you can quickly run multiple cases on it.
Another
I
question has
s-
come.
yeah, I see this. Is there any way to couple star CCM with OpenFOAM? But I don't know why you would want to do such a thing. This is quite a funny question.
Sir, there is also another question regarding CFD Force that it can
Mhm.
be used for overset topology.
Not right now. We have not added the option, but if you have observed properly, you will understand that you can modify any file in any folder. You have full access to all the OpenFOAM files. So if you can know the settings of your overset mesh, then of course you can just add those settings in your case and run it. And it will just run normally, like we changed the velocity and temperature boundary conditions. Similarly, you can change anything in the case and run it. So it is not a black box at all. Access of all the files have been given to the user.
Thank you so much, Mr. Nikhil, for being so patient and explaining many interesting things, many new things that will be very useful for the students as well as faculty members as well as CFD professionals. So it was a
Ye-
wonderful session, sir. Thank you so much.
Yes,
So
even I'm
if
very happy to be here and
yes, yes, if you have
I
any
am
further
feeling
queries,
very
they
good
can
right now.
immediately email. Yes, sir.
Yes, I said I'm also very thankful for the opportunity provided by IIT Bombay, and I'm always happy to come and share my knowledge here.
Yes, yes, yes. Yeah, we know that. And we are very much thankful to you. So
Yeah.
if in case they have any further queries, they can directly write to you or they can write to us and then we can direct it to them.
Yes, yes,
Yes.
sure, Pal.
Okay. Thanks a lot, sir. Thank you so much. So
Yes.
now we will move ahead with the demonstration part, the hands-on session. So I would request Paris to please continue the session.
Okay, ma'am. So first of all, thank you, Nikhil sir, for the wonderful presentation. Hopeful the students that have got a good idea about CAD and meshing. Before starting the session, I would just like to know everyone that today's session will be based on meshing. So, have you used any utility in OpenFOAM called Block Mesh or Snappy Hex Mesh? Or if you are working on it for the first time, so accordingly, I can settle my pace. So, if you can just type it in the chat box that you are new to Snappy Hex Mesh, we can move accordingly. Okay, new to it, new. Okay, so the presentation is made considering the new students only. Okay, just a minute. I'm sharing my screen. Is it visible? You answer?
Yes, Paris.
Okay. So, good afternoon, everyone. My name is Paris Palkar, and I'm working as a research assistant at FOSSI CFD team at IIT Bombay. And today's session will be on a detailed session using for machine.
So participants, kindly mute yourselves. Thank you so much.
Yes.
Yes, Paris, please continue.
So this will be a detailed session on meshing using Snappy Hex Mesh. So before starting, I would like to thank the FOSSI team for arranging such workshop, starting with Dr. Kannan. Dr. Kannan has just retired this year. He was leading this FOSSI project, and he was also a professor in the Department of Chemical Engineering at IIT Bombay. Dr. Chandan Bose sir. So Chandan sir is leading the CFD FOSSI project, and he is the PI right now. He is also a professor in the Department of Aerodynamics at University of Birmingham, and he is also serving as the visiting professor at IIT Bombay. And Payal ma'am is working as senior project manager in CFD FOSSI team, and she is the reason we are having such wonderful workshops. So let us start the session. So what is meshing exactly? So before the let us consider a industry. If you want to produce an output or product, you have to check the product is well suited or not. For that, the industry goes through various lot of process. It can be structural or it can be related to fluid as well. So we are dealing with the fluid part. So we'll be only discussing about fluids. So let us say we want to find out how this is the position of the cyclist, and we want to find how aerodynamically it is suited for him to be in a particular position so that he can achieve uh, the maximum speed. So there are three CAD models that have been generated uh, with three different parameters and position, and the CFD study has been carried out for the same using any CFD software. So, so what is Snappy X Mesh basically? Snappy X Mesh is an open form utility that is used to generate high quality meshes for complicated geometry. Only the thing is, this utility generates 3D meshes. So we have to create first a 3D mesh and then convert it into a 2D. There is a particular utility provided for that as well, and it is an iterative process where refinement can be carried out in particular regions of interest. So let's say I want to refine a particular patch meaning the STL or the domain of interest. I can do it using iterative process. We will see everything in short. And the mesh that is generated, it can be visualized or it can be accessed in the constant folder in the polymesh section of OpenFOAM. So, what is the workflow of Snappy Xmesh, or how can you start Snappy Xmesh? So there are two ways you have to start meshing. First thing is block mesh or external mesher that will generate your background mesh. So what do you mean by background mesh? We will discuss about it in some time. And the CAD model of which you want to conduct the CFD study. Once this background mesh is generated and the geometry STL file is created, it is not compulsory to have the STL file. You can have the object file as well, and there are various formats of the CAD file that you can import into Snappy. And once your background mesh along with the geometry it is generated, it is sent towards the Snappy Hex Mesh dict. Snappy Hex Mesh dict reads your background mesh and it tries to combine it with the geometry that you have created. And once Snappy Hex Mesh is executed, we get our OpenFOAM readable mesh that can be further used for your simulation. Okay, so what is the workflow or what is the idea of Snappy X Mesh? So the process generally starts with the creation of a background mesh. We generally use block mesh utility to make the mesh, and it is purely hexaedral and it defines the overall domain. And along with the creation of the geometry, like airfoil, bluff body, or any other geometry, let's say cylinder or flat plate, uh, the geometry is created. And once these two conditions are met, then we go to Snappy X Mesh, where the background mesh and the STL geometry are combined and is processed through the Snappy X Mesh dictionary. So before going to the CAD generation, the main interest is generating the background mesh. So there are three criteria that we need to define while generating the background mesh. If you are using block mesh, it is satisfied easily. But if you are using any external measure for this, so you have to satisfy these three conditions at least. So the first condition is the mesh must consist purely of hexahedral cells. So if you have seen the mesh in OpenFOAM, the mesh should be particularly of it should consist of hexahedral elements, and the cell aspect ratio should be 1. Along with that, there must be only single cell edge intersection. So it is meaning that two cells should not intersect in between. The edge of one cell should be intersecting with only one cell of its consecutive neighbor. Okay. So now moving to the Snappy X Mesh dictionary. So there are three main parameters of defining your Snappy X Mesh dict. Okay. Firstly, we saw how the background mesh is created. Then we saw how the geometry is created. Now our domain of interest is Snappy X Mesh dictionary. We will be visualizing it, so don't worry. You have to specify these three parameters in Snappy X Mesh in detail. So we will be we will be seeing this in just a while. But this is castellated mesh control, snap controls, and add layers. So what this castellated mesh control does is you have to specify your geometry, your refinement region box, or is there any STL file or geometry file that is there, and how it will be read by Snappy X Mesh. So you have to define the name of the geometry as well. And in snapping, what it happens is when you have your background mesh and you have your STL, so the Snappy X Mesh tries to snap the body inside the background mesh so that we can use it for the further simulation. And if you are working on external aerodynamic cases or internal flow cases, you can also use this add layers section where you can add the boundary layers to your custom patch. And there is also a section of mesh quality controls, but it can be added into a newer dictionary and it can be specified. Also, we can just add a fourth column and we can define the mesh quality parameters as well. I have written some small commands here. This will be helpful once we start implementing our mesh. So just be with me for at least 5 to 10 minutes and then we will go to the actual demonstration. So yeah, as we know, the background mesh, again, it is base level mesh. It is just a basic level mesh and it should cover entire of your domain. And this is the expected STL surface. It is an airfoil and this background mesh is generated by block mesh dictionary. Then what we do is when we run Snappy X Mesh, the second procedure that occurs is the refining of the background mesh. So the cells of our interest are refined in the particular patch. It is done in castellated mesh controls, and the edges of this geometry are defined by the surface feature extract dict. We'll also see about it. So how are the refinement level done? So if you do not specify any refinement level, it will just consider one single cell. But if you particularly provide a level 1 refinement, so it will be dividing it into 4 sections. And likewise, if you divide the section with level 2 refinement, so it will divide the subdomain into 4 parts. And again, the domain will be segregated into 4 parts further. So as we go ahead, various refinements can be added and it can be implemented. And then the removing of cells. So as we know, we have a background mesh as a different entity and the STL as a different entity. So we want the STL and background mesh to be together. So we do the removing of cells, unwanted regions are removed, and this is done by specifying a point inside the block mesh dictionary with the utility called location in mesh. So you have to provide a particular point in your block mesh dictionary where we want our cells to be retained, and there are two ways to define it. If you define it outside, it will be considered as the internal flow, but if you define it inside the patch or the STL, it will be considered as for internal flow problems. And this is snap mesh to surface means then the snapping of your geometry is done using snap controls, and we will see about it in few minutes. And this is the final step of your mesh generation, and you can add the boundary layers to capture the accurate phenomena that is occurring in your particular case. Okay, so before going to the tutorial section, I would like you to show how you can actually find any block mesh dictionary. So is my font visible, or should I increase it a bit?
It's fine.
Okay. Okay. So now, as we know, if I firstly you have to source your block mesh dictionary. Uh, just a minute. Uh, yes. Okay. Is it the screen is visible, right?
Yes, Chris.
Okay. Okay. So now we will be sourcing our homes dictionary, that is denoted by tilde. So we'll be sourcing it first. So we'll use the command source / dot bash rc. Then as I have two open form versions with me, as we have specified as well, it is always better to have two open form versions with you. So I have set an alias of open42412. It will notify me that your ESI version has been sourced and you are good to go working with the ESI version. If you want to source the foundation version, I have also created an alias. You can just write OF9 and hit enter. Sorry.
Paris, you can go ahead.
Okay. Okay. So here I can see the foundation version has been sourced, that is OpenFOAM 9. And if I want to source my ESI version, you can use the command that you have set in your bash rc of the home directory. And again, clear. And I'll go to my run directory. So run directory is the file location where your all the OpenFOAM 2412 files are executed. It is particularly denoted by your name or whatever you specify here, and you can run your OpenFOAM cases here. Okay, so I'll do ls. So if you don't know, ls command is used for listing out, and if I want to go in the fossee folder, I'll do cd capital F, and if I hit this tab, it will directly capture what I'm trying to write. Okay, in the fossee there are various folders, so I'll just quickly go in our topic of interest, and there are multiple folders. Okay, so if I want to find, I'll just write tutorials. So it is prompting key there is no folders called tutorial. I'll just source my homes/rc again. Okay, so now I am in the OpenFOAM example session. In the installation session, we have answered where the tutorial folders are generally kept, and this command, there is this command called grep -r snappy xmesh in the foam example. I'll explain it. grep -r. So what this command will do is, this grep is generally used as search. So we are interested to search the snappy hex mesh dict that is implemented in the foam examples. So when I'll hit enter, so it is listing out various files. If I do list out what are the tutorials that have been implemented, so if I list out, there are various solver, that is combustion solver, compressible solver, heat transfer, multi-phase, incompressible. So here you can see it will always locate key, let us say in the mesh folder. Do we have a mesh folder? Yes, we have a mesh folder, and in that mesh folder we have a utility called snappy xmesh in aerofoil naka 0012. So you can just check out if you want to find any particular dictionary that is implemented. This is not just limited to snappy xmesh. You can also try to use, let's say you want to find key, is there any solver? Because what we do generally in open is we try to see the tutorial cases first, and then we try to set up our own case. So if you want to just find rather than just manually going in particular folder into folder, what you can do is just write simple foam. So you are interested to know where is simple foam in your foam examples dictionary. Okay. uh, And again, it will list out which dictionary has used simple form. So you can directly go in. Let us say this CD is used to go in the particular folder. So let us say I want to go in mesh. I have hit a tab, so it has known what I want to write. Then I'll type snappy. It has again understood. Then I'll go in the motorbike case. Now I list out. So I have all these folders, and if I go in the constant, there are some files, tri-surface, turbulence properties, and transport models. If I go in system, so if I tell us, so there is this snappy xmesh dictionary. We want to test how it works. So you can just copy this into the run folder where you want to run your openfoam command. So now I am in my openfoam terminal again. I'll go in for C, and then so before that, so this foam clean tutorials command is used to clean all the case that was already existing here. So if I list out now, the case is clean, and we can see one on one what is happening. So this is of a complicated geometries, means before starting any complicated geometry, it is always recommended that you should start from the basic geometry first, and then you can go towards complicated geometries. So now for this, we are using the flow over a cylinder case. We will be just meshing it. We will not be solving the case here, but we will just be meshing it. So this is the domain. These are the approximate dimensions. We will be manipulating it based on our need. And the diameter of this cylinder is considered to be 0.1. Okay. So when I go in the geometry making of this geometry can be easily replicated into FreeCAD. And then either if you want to export it in the form of object file, you can do that. Or if you want to export it in the form of STL, you can do that as well. There are various commands or the various extension that the folder reads. And here, if you are able to see, I have used the diameter of this cylinder to be 0.1, but here I have specified it the 0.1 mm, and here I have specified the geometry as 0.1 meter. So like you might be thinking ki there is some discrepancy, but just to tell you ki OpenFOAM generally reads only the data that is related to that is in meters. So even if you make your geometry in meters, it will be read by OpenFOAM and PyReview in terms of meters only. It will not read it in mm. Okay. Again, there is surface transform points. We'll come to it later. So I'll do list out. And again, so if you can see, this is the general case structure. If you want to visualize it on OpenFOAM, you can do that as well. You have to just write tree, and it will list out what are the features are there. So this folder generally contains your boundary conditions. These are the all run and all clean files that will be executed if you want to run the whole case without knowing what is happening. This is the try surface folder. In try surface folder, we generally keep our STL that is being exported from any CAD modeling software. Let it be SolidWorks, let it be FreeCAD, or any other CAD modeling software that you are interested. You can just go to this try surface folder and you can paste your uh, STL of your interest. And there is this extended feature edge mesh tip. We will understand what is this. Then in the system folder, there are multiple files again: block mesh dictionary, control dictionary, decompose path, extrude mesh. And out of these dictionary, only few we are going to use today. So that is block mesh, uh, your snappy hex mesh, surface feature extract, and at the end extrude mesh dict. As I told, snappy hex mesh is just a 3D meshing software utility. We cannot use it to generate 2D meshes, so we have to just use an extrude mesh utility in the OpenFOAM. It is provided by OpenFOAM itself. So you have to just run this extrude mesh command, and you will be able to see the geometry that is created in 2D. Okay, so let us start. So firstly, if you can see all run, as we are running out of time, I won't spend much time on explaining all run file. We'll just try implementing the keys. So firstly, in any CFD simulation, the first step is the CAD generation and the second step is meshing. So now we will be using block mesh. So it has created blocks, and there are four patches. Four patches are generated. They are namely outlet, fixed walls, front, back, and we can, if you want, you can also add top and bottom, inlet, etc. So you can add that as well. So if I want to visualize it, I'll make a folder with an extension .foam that will be readable for Paraview. So for creating that, I'll just write TOCH touch foam. I generally use foam. You can write anything. You can write CYL cylinder. You can write your own name as well. So I have written foam.foam. Now my foam.foam file is generated. I'll just navigate to it. Uh, I'll refresh it. So the foam.foam file is generated. I'll go in the Paraview and I'll try to visualize it how it looks. Okay. Okay, so we are in the Paraview. I'll open the folder here. So this is the solid color. If you want to visualize your mesh, what you can do is in the ribbon, go from surface to surface with edges. So it has created a finer mesh, and now I'll just reduce the opacity, and we will try to visualize how our STL geometry will look like. So now this geometry is very much transparent. Now we will try to implement, or we can try to see how the geometry is looking. As I told, we have to keep the folder in the try surface. So let us try to open this cylinder.stl. Let us open it. Okay, so as we are able to see, this is a 3D geometry. This is the 3D geometry, and it will look like this. But let's say you want to move it a little bit further. Just a minute, I'm on the axis grids. Okay, and this is the 2D view, 3D view. If I want to switch to the 2D view, what I can do is I'll hit the this ribbon, and now the view is 2D. So right now it is at -5, -15. And what if I want to go +5? So I want the geometry here. So there is again a command called surface feature transform. I have surface transform points. I have mentioned it here. So I'll go in the constant, and in constant I'll go to try surface and I'll list out. So if you are new to any particular command, what you can do is surface transform points and hyphen L. So it will list out what you want to do. Means there are various commands that you can execute with this surface transform points with the options that are available here. There are multiple options that are available, and in the output you can give the surface file in as input, and you will get the output file again as the surface file. Okay, so now I have this cylinder.stl, and the cylinder.stl is at -15. So we'll just try to move it further. So what I'll do is I'll do surface transform points translate to, let us say, I wanted 5 points ahead, 5 meters ahead. So I'll give +5, 0, 0. As input, I'll give this file cylinder.stl. cyl is just the short form, cyl.stl. And as output, I want, let us say, you can define it on your own. Let us say cylinder3.stl. There is just a minor correction. Okay, so it has readings. It read the surface from cylinder.stl and it has written it to the surface.stl, cylinder3.stl. It has translated it and it has ended. So we can visualize it in Paraview as well. 1 and 3. See, so the geometry has been translated to -10. So let us say if you make some change, some errors while making the geometry, you can rectify it using the commands that are inbuilt in OpenFOAM. Okay, so this part is covered. So we have now generated the background mesh, and we have also generated the cylinder as well. The cylinder is generated using FreeCAD. It is an open source CAD modeling software. You have to just specify the diameter in a XY plane. Just keep in mind that the XY plane here and the XY plane in the block mesh dictionary should be same, so that you can visualize your geometry likewise. Or if you made your geometry in YZ plane and you have made your block mesh in XY, so it will throw some error. So just be careful about it and you are good to go. You have to just extrude it in a particular direction, and you can work on it for your meshing. Okay, so this is the background mesh, how it looks, and this is the geometry of the cylinder. Then the certain commands to run. This is block mesh. We have seen block mesh. We'll be looking at surface feature extract. What surface feature extract is? This surface feature extract command is only for OpenFOAM 2412 or the ESI version. If anyone is using OpenFOAM 9 or Foundation version, they have to use only surface features. You can the command for command in OpenFOAM 9 is surface feature, and in OpenFOAM 2412 it is surface feature extract. Okay, so let us go now to the surface feature extract dict as well. You can use any of your notepad visualizer, but as I'm more comfortable in Visual Studio Code, I have installed it, so I'll just open it in VS Code. It looks good and you can edit it as well. So just change this to C++. Yes, so here
Can you increase the font size?
yeah, sure, sorry. Just a minute.
Paris, just I'm interrupting. So we have just put the attendance link now. We can just take a break for 1 minute and let the participants mark themselves present, and then we can continue.
Okay, ma'am. So like, is it visible now? Is it better? Wait, is it better now? Even sir or Payal ma'am can just.
Yes, Paris, it's visible.
Okay, okay. Okay, I'll wait for some time. Uh,
Okay, Paris, you can continue. Most of them are done.
okay, okay, sir. Okay. The screen is visible, right?
Yes.
Yes.
So whenever you open any open form file, so this is the general thing that you will be watching. So in the form file, this will tell you as the two, and the format of this file is ASCII, and this is a class. This is a dictionary, and what is the object that is used in this dictionary is surface feature extract. Now let us go to the surface feature extract dictionary, exactly what it is. It is not a bigger dictionary, it is just around uh, 20 to 25 keywords. So firstly, you have to define your STL, the same STL that you have inputted in your tri-surface dictionary, and you have to tell which extraction method that you want to use, that if you want to use it from surface or volume, etc., it can be used. You can also extract it from the edge as well, and the include angle. As we are running late, I cannot, I mean, I have the visuals ready for this, but we are running late. If we get time in the evening slot, as I'll be only presenting this session, I'll demonstrate what is the significance of this include angle. Then the subset features, uh, that do we want more than one or two phase connected in this. So when Nikhil sir said in his previous session that you can use CST multi-region form for heat transfer related studies. So whenever we make multi-region meshes, we use this command to true, and open edges, that as we want our edge to be kept as one with the consecutive neighbors, we have written it as yes. And write object, so it writes the object as emesh in the tri-surface folder itself. So I'll just run the command now. Let I open the terminal. Okay, so I'll write. Now I'll just write surface feature, and this has given me feature, and now I want to extract. Okay, so it has written this particular file, the STL file, into an image file. Why this image file is important, we will see in the snappy xmesh utility. The execution time was 0.1 seconds, and the clock time was 0 seconds, and it has ended. It has written everything. If you write tree here, so here you can see this cylinder.emesh is generated. You can also generate the e-meshes for this cylinder 2 and cylinder 3. The only change is you have to specify the this name in your surface feature extract dictionary. So this will be changed to cylinder 2. Okay. So this will be the name, and you can generate the image for this particular folder also. Just keep in mind, name the file that you are intending to make the meshes of. Okay. Okay, so now let us go to our Snappy Xmesh utility and understand everything in detail. Just you can just drag it and keep it here, and just yeah. Okay, so this is the Snappy Xmesh dictionary. Uh, Again, it is written. The format is ASCII, the format in which it is written, and it is again a dictionary, and it is an object that is written in the dictionary. So whenever we type the Snappy Xmesh command, our terminal will catch it and try to execute this dictionary only. Okay, so as I said in my presentation, there are three fields that you have to enable: castellated mesh, snap controls, and add layers. So these are set to be true. You can always use false to turn to switch off the any particular uh, domain if you are not interested to use it as of now. So what we can do is we can use false for add layers, and we can save it as of now. So we are not generating any layers right now. We will be generating as we move forward in the tutorial. So then comes the geometry section. Again, you have to define your geometry, the geometry that you are using, and the same geometry that has been used in the try surface. Again, it describes all the input geometry required by Snappy Xmesh, and this is the file name of the geometry that has been placed in your try surface. And we are asking it to read it from the type is try surface mesh, and we are asking it to be named as CYL cylinder. uh, you have to specify it here, because we will be using this patch as CYL only further as well. So in the geometry section, we can add two, I mean, we can add multiple refinement box, but as of now, we are just using two refinement box. You have to just specify the minimum and maximum coordinate for your refinement box. And once you execute Snappy Xmesh, it will start to add the refinement box in your particular region. Okay, again we have added second refinement box. So generally refinement is given in aerodynamic cases to capture the wakes that are occurring in the external aerodynamics cases, so that we can capture and model it very accurately. Okay. So now let us go to the castellated mesh controls. This is the second part of your first part of your Snappy Xmesh. So it controls the refinement parameter. So there are some entries that I will explain you. So this is maximum local cells. So the 10,000, it represents the total number of cells your single processor will use, and these are maximum global cells. So this is the total number of cells that are allowed in your total simulation, you can say. Then minimum number of refinement cells that are used 10 here, that are required per iteration. If you want to refine 10 cells, at least they are required. If we do not satisfy this criteria, the Snappy Xmesh will crash. And this is max load unbalance. So let's say if you have local cells and it is exceeding the amount of 10,000 cells per processor, what will it max load unbalance will do is it will try to segregate it to other processors, so that 10% usage is divided to another processor as well. This generally comes in place when we are running in parallel. We will be looking for serial and parallel as well. And if we want any buffer layers between different levels, so yes, we want. So the entry is n cells between levels, and we have kept it as 10. Okay, so now in the castellated mesh, there are features in the sense file, means what features that we want. So the file name is cylinder.emesh. It will read the image from surface feature extract that we have generated, and we want the refinement level of 2 for our image. Okay, and then we will go to surface based refinement. So it will refine the cylinder that we have, and for cylinder patch, this is the same name that we have given it in the geometry section as well. So this is user specified name, and again this is user specified name. Okay, and now we want the level to be 5. uh, Again, here there is a catch. If you are using OpenFOAM version 2412, you have to specify it in the terms of close brackets. But if you are using OpenFOAM 9, you can just simply prompt a single number and the mesh will be done. Okay. So now resolve feature angle. So if there is any edge refinement, so if you want to capture it or not, based on this the feature angle is given. Then refinement region. Refinement region is particularly given to a particular region. So there are two regions. First is refinement box 1 and second is refinement box 2. So there will be a second level refinement, as we can see in the presentation. The blocks will be divided. Every block in the particular refinement region will be divided in two levels at least, as we have fixed it. We can change it as per our need. Again, refinement box 2, this is also same as 2. And where we want it as inside, there are three parameters that you can specify: inside, outside, and there is one more parameter as well. And location in mesh, this is, you can star mark it. It is very important parameter. If you misinterpret this particular filter or this particular line, your whole SnappyX mesh will crash. Okay. And if you can see, wait, let me show you my, okay. Is the screen too much confined?
Yes, Paris.
Okay, so I'll visualize it afterwards. Just for right now, I'll just explain what is the blockmetric dictionary. And if we want freestanding zones, so means if there are any bound or there are any domains that are not part of our geometry, this freestanding zones, it considers them as well. So now we'll go to the snap controls. This is the second part of the SnappyX mesh dictionary. So there are various entries. So first is smooth patch. So if we want smoothing iterations on our patch, so what level of smoothing iterations we want on our patch, so it is defined as 6. And while snapping, what should be the tolerance between two cells? How close the points are required to be snapped when we are converting the STL? That means when we are merging our geometry background mesh to the cylinder, what should be the tolerance of the 2 points that we are trying to snap? Okay, then this is n solvator. So it decides the mesh displacement relaxation, and these are relaxation parameters for meshing. And if we want edge based snapping, let us say you are working on an airfoil or something, or as we are working on the cylinder case, we have an edge, so we will give this feature 15 for the n feature snapper, and implicit feature snap and explicit feature snap. So this is something that I mean, you can, if you turn on implicit feature snap, SnappyX mesh will try to read the geometry on its own. But if you turn on the explicit feature snap, we have to define it in the upper region that we have mentioned, cylinder. This is user specified geometry. So if you want to specify the geometry in your SnappyX mesh, you can specify it using explicit features. But if you want to SnappyX mesh to capture it on its own, you can just turn on the implicit features as true, and then add layers. So as of now, we have turned the features of add layers as false. We will be not, the whole add layers features will not come into the place. So this will not be useful. So let us go to the terminal, and now we can write snappy x mesh. This override commands, what it does is it will help you. Okay, x mesh, right? So what override command does is it will override any existing, if you have run any SnappyX mesh feature previously. So if there was any mesh earlier, it will be overwritten by this command that we are using. This should be done within some time. Let us wait. Okay, so this mesh is generated in 22 seconds, but the paraview is looking very clumsy. So what I'll do is I'll just turn on this as well, layer control as well, and we will run the snappy x mesh again. So there was one snappy x mesh that was used without adding the add layers feature, and now we are again using the snappy x mesh feature with layers. So I'll again just write snappy x mesh override. It will erase the existing mesh and write the one again. So it should be done within some time, 20 to 40 seconds max. Let us wait. Okay, so the mesh is generated in 20 seconds, and I'll now just zoom out a bit. Is the paraview visible now, Ivan sir?
Yes, sir, it's visible.
Okay.
Yes, Paris.
Okay, sir. Okay. Thank you. So what I'll do now, I'll just go in the folder section and I'll open the foam.foam file that I have, and I'll hit apply. So now the geometry is done. We can also see it. So the snapping is done quite well. If the snapping is not done appropriately, there will be some cracks that you will be seeing here. But our snapping is done very good. So you are not, means there are no visible sign of mesh cutting. So I have just switched to the 2D view for better visual purpose, and I'll just now showcase surface with edges. So now there is one refinement region that has been added, and inside it, if we can zoom more further, I hope you are able to see the boundary layers that are occurring. So we have specified the number of boundary layers to be the boundary layers are expected to be 4 with the minimum thickness of 0.01. How this has come, I'll also discuss about it. So I mean due to my limited RAM as well, I'm not able to go much further. But if you are able to see, you can see the boundary layers are being generated in this region, and the further refinement is also done in your total domain. Okay, so your mesh is generated, but you are not sure about it. Is it good enough or not? So what you can do is you can go in your terminal and just use the command check mesh. So this check mesh command is used for checking is your mesh good enough or not. So it is checking and it has prompted me the mesh is okay. You can work with it further as well. Also, it will list out what are the patches that it is using. We have specified them in Snappy Xmesh dictionary, and the details of the patches as well. Okay, but the thing is, you won't be able to visualize it in ParaView. Let's say you want to visualize it as well. So what you can do is there is a command check mesh -help. So it lists out what are the existing commands that you can use. So for this, we are using write all fields. What this command will do is write the fields with mesh quality parameters. Okay. So what I will do is check mesh write all fields. It is writing. Okay, it has ended. Now I'll go and just refresh my file. It is happening. Okay, and now let me just skip the zero time. Okay, so now you will be able to see various parameters that we have given in the m- um, mesh dictionary. You can read about it as well. If you want to, let us say you want to check the aspect ratio, and so here the aspect ratio is near 1 to 2. You can zoom it a bit to see if there are any uh, if their aspect ratio is increasing or not. So I don't think the aspect ratio is increasing as of now. There are some other parameters as well. What is the skewness of this mesh? So it is basically some skewed, but it is not in the domain of our interest. The cylinder, it is very much pretty much okay. You will be seeing some skewness due to the boundary layers that are generated, but you don't have to worry about that. Okay, and you can also visualize orthogonal angle or thickness of the particular cell. You can list out every parameter that you are interested in. Okay, so this is our mesh. This mesh utility is being used using serial processing. What if I want to run the mesh in parallel? So again, you have to do nothing. Just go in, and here it is cylinder mesh dot parallel. There is only a change of command. I'll show you. So all run parallel. What it will do is it will run all of your domain in parallel. Wait, let us do it. Let us wait. It will take some time. Okay, it is running on all run. I want to run it in parallel. So it has called MPI. It is used for running parallel simulation, and we'll just wait till the parallel simulation parallel meshing is carried. So it is reconstructing. Okay, so extrude mesh is done. So if you can list out, it has decomposed your domain into 4 processor, 0, 1, 2, and 3. So we can see what is happening here. We need to also make a foam file to visualize our mesh. We have created the foam file. Just copy it and paste it in every processor that you have. There are 4 processors, so we are just pasting our foam file in the 4 processors to view which processor is handling which mesh. Okay, so now I'll go in file again, and rather than working in this case, I'll go to the parallel mesh, and in the processor there is 0 processor. I'll open this file, apply, and it is coming out to be some weird, so I'll just give it surface with edges and color it with red. Okay, and double clicking, I'll just change the name of it as 0 processor. Okay, now I'll open another second processor, 1, and I'll hit apply. Okay, so it has constructed something. Before going there, we'll just change the name to processor 1 underscore. Okay, so we will open the third and fourth processor as well. So now it has showed something. We'll again write it as third underscore processor, and we'll now open the fourth processor. Okay, and apply. Okay, so it has captured all the domain _4 _. Okay, so what we can do is, this is the 0th processor. This is your first processor. I'll change it to surface with edges, and I'll just color it. Let us say yellow. So this is your yellow domain. This is your third processor. I'll color it with green. So it is using green. And this is the fourth processor. Let us pink it with color it with pink. Okay, and change it to the surface with edges. So here you can see there, in the previous case when we were running it on the serial, the single processor was tackling the whole domain. But once we have decomposed it, now 4 processors are taking care of it. So we can see the regions as well. Okay, and if you want to load the foam.foam file, you can load it. Hit apply, and just as we have reconstructed it, here you can see reconstruct par. So there will be an issue, but if you are not using reconstruct par, you have to just write decomposed list. Okay, so we can see our mesh. So I'm just winding up due to time limitation. Just a minute. And the last utility that I want to explain you guys is the extrude mesh utility. I'll open it. So it is again very small utility. This utility converts your 3D mesh to 2D mesh, and the name of the input STL that we are using, that is cylinder, and we want it to extract from the surface that is present, and this is surface feature extract. Just a minute. Yes. Okay. Yeah. I'll try zooming it. I hope the code must be visible. Can anyone confirm?
Yes, Paris.
Okay, so this is the extrude mesh utility, and you can basically convert your 3D snappy X mesh to 2D snappy X mesh using this utility. So we want to construct it from patch and source case. If you have a particular, let us say you want to extract it from this particular address, you can use this. But as we are in the same directory called cyl mesh, and we want to extrude this mesh only, so we are not using any address. You can just give a dot and it will work. And source patches is the which patch do you want to extrude. So it will be the front patch, and what patch will be it exposed till the extent it will be exposed, so it should be back. And how we want it, so we want it linear normally. Let us say oh, okay, so this is our domain. Wait. And I want it to be extruded in the 0.07 meters in the linear direction. So I can specify this in this particular section. If I turn negative, it will be just it will be extracted in the frontwards. As I have given positive, it will be extracted backwards. And flip normals, if you want to flip the means it is just basically opposite of where you want to locate your mesh, means visualize it. If you flip it, the extrusion will be done frontwards. If you keep it false, the earlier commands will be taken place. That's all from my end. Actually I had some things to show, but as we are running out of time, I feel like we should stop. anyways, in the second session, I am going to present the heat transfer case study. So we can discuss more about meshing as well as heat transfer in the Q&A session. I have prepared some post-processing visuals for you guys as well. So we can have a discussion on it also. Also, if you have any questions, you can post them in the chat box. But as I can see, it is 1:10 already, and at 2, Mr. Harish sir session will be starting. So let us take a break, and we can meet in the next session. Is it okay, Payal ma'am?
Yes, absolutely fine. So, whatever questions you have for Paris now, you can just note it down somewhere. And after Harish's session and the next demo session, we can take it up. Okay, so we should break for lunch now. Otherwise, for the next session, we'll be late. So, because we are breaking at around it's 1:10 now here. Yeah, 1:10. We can start the next session at around 2:15. Okay, so by 2:10, please try to join. Then we can start at 2:15 the next session. Okay, so we are breaking for lunch now. Thanks a lot, Paris, for the presentation.
Thank you, ma'am. Thank you,
Yeah.
everyone.
Thanks. Bye. See you in the after post lunch session.
Yes, ma'am.
Bye. Everybody, very good afternoon. Mr. Harish Jairaj has already joined, but we will be starting in another 5 minutes because we are expecting more participants. So welcome, Harish.
Yeah, hello, ma'am. Good afternoon.
I can also see Professor Sandeep Juluru has joined. So welcome, Professor Sandeep. So just like we have the advisory board members for the CFD team of FOSI, we also have a team of professors, a group of professors who are a part of the FOSI team. We call them as faculty partners. And they actually guide the students for the internships, fellowships, and they also take workshop sessions. And they replicate everything that we do at IIT Bombay for the FOSI project. So Professor Sandeep Juluri is one of them. So let's wait for another, say, 1-2 minutes, a couple of more minutes. So actually, Harish, we are expecting around, more than 150 participants. In the morning, it was around 170. And towards the end of today's session, the count was around 200.
Okay, ma'am.
Yeah, so let us wait because they'll, otherwise they'll miss some part of the presentation.
Yeah, understood. Okay.
Okay, thanks. So we have 118 participants. I think we can start now. Let them join gradually. So first we'll have your introduction and then we can start the session. So Deepak, you can start the recording on the YouTube live. I hope it is already started.
Yes, ma'am.
Yeah, no, I'm asking the eStudio team whether they have started the recording and the live streaming.
Ma'am, live is on. I'm not
Yes,
sure.
ma'am.
Yes.
Recording will be start.
Okay, fine. Fine. So first of all, I beg your pardon because I am used to call Harish as Harish and not Mr. Harish because he used to be one of our FOSI interns. We had worked together as team members. Harish used to be our employee at FOSI IT Bombay. And now we are actually very much overwhelmed that he's doing so much good in his career, and today he's one of the esteemed advisory board members of FOSSI. It's really very much overwhelming to witness such a growth. So congratulations, Harish.
Thank you, ma'am. Thank you very much.
Yeah, and let me introduce him to you all. So Mr. Harish Jairaj is the founder of Codynamics. He's a CFD engineer with expertise in ANSYS Fluent, OpenFOAM, and numerical modeling. His work focuses on utilizing commercial tools and customizing open source solvers for industrial and research applications, particularly in multi-phase flows, HVAC, and external aerodynamics. Alongside his engineering practice, he is a Python developer specializing in desktop software development for scientific computing, building tools, and enhancing simulation flows. Mr. Harish also contributes to the CFD community through Codynamics, an initiative dedicated to creating structured learning resources, tutorials, and practical content that make OpenFOAM and applied CFD more approachable. Through platforms like Udemy and YouTube, Codynamics has helped learners worldwide to strengthen their skills in CAD, CFD, and scientific computing. With a long-term vision of advanced CFD technologies, Mr. Harish is committed to developing innovative solutions and creating platforms that bring in high-end simulation tools closer to engineers, researchers, and industries. So, yeah, here is he in front of you. So, very soon he'll be presenting his session today. And we are really thankful to you, Harish, for joining the session.
Thanks for the introduction, ma'am. Yeah, very glad to be
Yeah.
back here.
Yes, we are also very glad. So over to you. You can start the session.
Okay, ma'am. Yeah, just a minute. I'll present my screen. I hope my screen is visible, right?
Yes, sir.
Yeah. Okay. Thanks for confirming. So, I'm Harish Jairaj. I represent my small startup, Codynamics. So, here I'm just going to give a small talk on potential use of CFD for enhancing HVAC designs and application. This is not going to be very technical. I'm just going to try to give a spark in the participants to try out HVAC CFD in general. Because when I started with CFD, most of the people and most of the tutorials online were focused on aerospace and mostly mechanical. So when I mean mechanical, it's mostly automotive, aerodynamics and such kind of simulation. But as in when I moved to industry, I realized that there is huge scope for HVAC, especially in a country like India, where we are trying to build a lot of buildings. HVAC designs is very much necessary, and there is a huge scope for CFD here. And apart from aerospace, I just want a lot of people to try out HVAC, and if it interests them, I just want them to pursue in that direction as well. So my talk is mostly going to be exploring a lot of domains within HVAC, and people might not even know that these are actually part of HVAC. I mean, what is HVAC? HVAC is heat, ventilation, and air conditioning, but it's not just restricted to that. There are many applications that is bringing in design optimizations and so on, but many people who are learning CFD or exploring CFD might not know. So I hope it makes a change after my presentation. So the overview is going to be why simulate HVAC with CFD first of all. So if you take a CFD case in general, we do it because experimentation is expensive. So when I mean experimentation, if you want to build an aircraft or a car and do the aerodynamic analysis in a wind tunnel, then it's going to be very, very expensive. So we brought a numerical method where we can do the CFD and iterate on our designs, and we consolidate the designs. Let's say we have 50 designs, we consolidate to 5 to 10, and then we manufacture and test only those, because numerical simulations are going to have errors. But think about a building. At least a aircraft or car, you can manufacture 5 different things, and then eventually you can choose one and put it for mass manufacturing. But what about the building? You can construct it only once. So CFD becomes very, very necessary to avoid a lot of hassles in constructing, demolishing, or saving a lot of cost. So it is very essential to do it very accurately and provide a valuable resource to the architects and the engineers, the civil engineers, to make the overall building comfortable to live in or work in. So we will just look at many applications where HVAC simulations are coming in. So as I mentioned, HVAC is heat, ventilation, and air conditioning, but there is another component called refrigeration, HVAC and R, but usually it's known as HVAC or HVAC. So I'm just going to keep it that way. We are not going to look at refrigeration. And just to start with, as you might already know, you have seen, I think, 2 days of lectures. You have seen a lot of domains apart from aerospace as well, like hydraulics and everything. Very differently, this kind of simulation is going to give a different perspective. Like, we are not going to just see data out of our simulation, but visualization matters more than the data here. Of course, the data like temperature drop, the pressure drop, the contaminants are going to be necessary, but visualization plays a huge role in HVAC. I'll try to explain why it is in that way as we look through the slides. So you know what is CFD by now, and the key goals in any HVAC simulation is to ensure thermal comfort and indoor air quality. So when I talk about buildings, buildings are not going to be aerodynamic in a lot of senses, as you might know. So what do we actually look at the simulation? So we want to ensure the thermal comfort, because when you are going to live in, you want to feel comfortable, and indoor air quality. As we move towards the climate change and the pollution, we are more focusing on indoor air quality now. And we also have to improve energy efficiency. Just because we want to keep more air quality, we cannot keep running air conditioners all the time, because the energy is going to be overheating, and that's going to be expensive, and it's eventually going to cause more damage to the earth. And we also have to optimize airflow distribution and ventilation, because even though you have fans, natural ventilation plays a lot of role to give you proper comfort. And we also have to evaluate alternative HVAC designs before deployment. As I said, constructing and feeling bad is not a choice here. So we have to make sure everything is perfect, and then we have to start the construction. So major types of CFD simulation in HVAC is very broad, but if we have to classify, we can basically put it to 5 different groups. So we can see the first type would be airflow and ventilation simulation. This is the most common type of ventilation simulation that we would be doing with any type of HVAC simulation. So the objective would be to model the airflow behavior, and we will be looking at the velocity distribution, recirculation zone, and optimize diffuser vents and duct placement. So these are not something that we would look in a daily basis in a construction or a house. If you look around, you will not be able to see this a lot, because we are not focused on that. But if you take a data center, office, high-rise buildings, then they are very much cared about the velocity distribution, because you should not feel very uncomfortable when you enter a room. If the air is just blasting through the ceiling fans, you're not going to feel very comfortable. And if you take a data center, then the heat generation is massive, and you have to properly vent it out. And if you are in a high-rise building, then you are going to have something called a AHU, air handling unit, which is mostly kept underground, and it's the basic chiller unit. It's like centralized. Uh, all the HVAC components are going to cool your air and then push it through the entire building. And during this process, the pumps are going to heat up, the temperature is going to rise in the air. And this is a whole lot of problem, because whatever temperature you are bringing into the air, it's not going to be supplied eventually. So this whole problem can be solved only with simulation, because if you try to experiment, it's going to be expensive. And the second type is the thermal comfort analysis. This is where we are getting close to our daily, whatever we are seeing in our office or houses. So if you take the thermal gradients or predictive mean vote, it's a mean vote is might be a new term. It's like if you put 100 people in a room and you set a temperature, and if you get a vote from the people, like how comfortable are you feeling in a scale of -5 to 5 or -10 to 10 depending on the study, then what is the rating that you're giving? So this is like a comfort analysis, and the opposite is the PPD, which is the predicted percentage dissatisfied. So we have to take these data and then we have to simulate in order to see how comfortable someone might feel on an average inside a room. So this is mostly useful in office rooms, passenger cabins, and classrooms. And if it's a big university and you're building a big classroom, then this is very much necessary, because if you think of a huge room, the air vents are going to be close to the walls, and student sitting there might feel very uncomfortable, while someone sitting in the middle is going to feel very hot. So you have to properly look at the recirculations and how far your airflow can move, or should you place some inlet at the middle of the room in order to keep the temperature uniform. So now we are getting closer to what we would see in a daily. But even further, if you look at the indoor air quality, that's the third type of simulation, we are bound to see it everywhere. So if you take hospitals or clean rooms, laboratories, or as an engineer, if you are working in a manufacturing facilities, then these kind of or even hotels or restaurants, you can see this kind of simulation coming in if it's a big hotel. So this models the simulation of CO2 dispersion. So if you are in a confined room, like a hospital, you don't want external air to be coming in very regularly. But even with an air conditioner, your carbon dioxide buildup could be slowly creeping on you, and it can cause problems. And if you are in a restaurant where there is, maybe they are storing alcohols or some kind of spirits while cooking, so that's VOC, which is volatile organic compounds, then these kind of volatile liquids can evaporate in room temperature or pressure, and it can disperse, but you don't want that to happen. So how do you contain that very locally without a refrigerator, even if you store in normal condition? And these kind of simulation come in IAQ, which is indoor air quality. And then there is the energy performance simulation, where we couple simulation to heat loss or gains. So let's say you have a big factory and there is a generator running. You want to push the DG air somewhere where it will not affect the factory itself. If you're pushing it very close to the factory, it's again going to heat up the indoor air and it's going to be bad. And the other part, because it is heating very regularly, you're not going to get the maximum efficiency out of the HVAC machine. Let's say you have a data center and your chiller is not working fine, then it is a problem. But what if the chiller is working fine, but the heat of the chiller is actually affecting your entire room temperature? Because chillers are usually kept on the roof. So this is again a big problem. So how high do you want to keep the chillers from the roof so that you don't get bad effects from it? And this is energy performance simulation, but it's not confined to this alone. Let's say you want to build a room and you want to keep ACs. How many ACs do you keep to optimize the airflow? That's the first part. But as you increase the air conditioner, you're going to get more comfort, but you're going to lose more energy. Like you're going to consume more energy, which is again bad economically and globally. So you have to also optimize that in a sense so that you get a trade-off between the energy consumption and your comfort. So you cannot just prioritize either of them. So it has to be a trade-off between both. And comes the last one, which is the system performance. It's mostly not related to CFD, but since it's type of HVAC simulation, we are putting it here. This is more like a circuiting, let's say a MATLAB kind of simulation, where you have a whole lot of system. In a manufacturing facility, if you see, they are not going to get the usual voltage or wattage with regular frequency. They're going to get higher, and some components might need higher voltage. Some components might need less. So you must have electrical regulators so that sudden voltage hikes are not there for certain components, or else our compressors, impellers can fail eventually, which is not a good thing in a confined scenario, right? Because most of the HVAC components are going to be within a confined room or inside the walls. It will affect the whole manufacturing facility. So these kind of simulations also exist apart from CFD, but just wanted to cover it. Now, HVAC isn't limited to air conditioning ducts as we might think. It's wherever there is air, temperature, and comfort. So let's take a very small example. You're hopping onto a car and you feel comfortable when you turn on the AC more than when you just have your windows open. It is because we know how the air vents distribute the flow to the passengers, how the defogging works when you are in a different temperature condition. If you have a heater on in your car and there is rain outside, you're going to get fogging. So how do you defog the windshield and what is the optimum temperature? So these are not for the regular users, but for the manufacturers or the designs, the automotive designs. Those teams are going to look at this kind of simulation, and this is very huge in India. And all the manufacturers are looking through this, especially for the windshields and the headlights, because fogging on headlights is not a good thing. And then there is also a small part of how the sunlight affects the cabin temperature, because although we can put tint sheets on the windows, there is a government regulation on how black can your windows be. So again, it's a trade-off. So we have to see how much of light can it pass through, what should be thickness of the glasses. So there are radiation and there is light directly affecting. So we should also have a trade-off between the light and the radiation. So this is very small. And if you just go slightly wider, you can see trains and aircrafts doing similar kind of simulation. At least in trains, when the doors open in a metro or something, we can get fresh air, but it also takes in pathogens and pollutants inside. So we want to avoid such kind of scenario, and we bring in air curtains there. So if you enter some hotels or shops, you might have seen they would have had air curtains in the entrance. So such kind of air curtains are usually kept in the entrance of aircrafts or trains in order to avoid external pollutants coming in, because it gets very hard to remove. And then, as we already saw, we have data centers where we have the hot aisle, cold aisle, where we don't have a lot of forced convection. Instead, we have to take the thermogradients and look how we can provide the vents in such a way it naturally convects in order to reduce the energy consumption by the HVAC components. And we should also ensure server reliability, because as you might know, data centers are semiconductors, and when they heat up, they don't perform very well. It can crash. So we have to keep the temperature in a controlled range, and air conditioners alone are not going to be very helpful in a data center. There is a whole lot of simulation like chilling, and there is a vent simulations, there is forced convection sometimes. And coming to the last part, which is the office or classroom spaces, that's even bigger, and we have to ensure balanced air distribution, because if there is CO2 buildup, it's not good. If it is also heat buildup, it's again not good. It's not going to be energy efficient in comfort zones, especially if it's an office, right? So here I have two images showing two extremes of the simulation. One is extremely large indoor simulation, like a stadium where it is open, but you should definitely provide air conditioning so that the people don't feel it very hot. Anyways, the air is going to get hotter because it's open stadium. Still, you have to provide the air conditioning. So what should be the temperature in order to make them feel comfortable even when the temperature is not contained? The other extreme is the external airflow around a city, where if you are constructing a building or if you are taking an office at some floor in your in a big building, then how do you optimize the airflow? Because we will get the data from the observatory or satellite data on how the wind changes throughout the year. So you can optimize in such a way that you can make use of natural ventilation to some extent, but there is also wind movement, so that when you open your windows, it should not blast your windows, right? There are other components as well, but I'll just keep it to very basic, which is the external flow, where you are trying to optimize your construction or office placement windows based on natural airflow. And again, as I said, the door curtain systems, this is very important in a lot of places. And as a manufacturer, they will do the simulation, not as a client, but because it becomes a standard in a way. So once you manufacture for certain size, it's going to stay the same. But there are a lot of energy efficiency optimization to be done here, because it has a rotor part. It wears out soon, and there is also a motor. So you have to optimize the energy in such a way, or optimize the design in such a way you get maximum airflow even for low RPM or low energy consumption. And the other extreme is CO2 spread. Let's say through the air curtain somehow people enter, and then there is CO2 spread inside the hall, like a concert hall, because there is no vent outside. These are mostly acoustic optimized buildings or hall, where there is less number of vents so that the sound doesn't go out, or it's contained. It's designed for acoustics. So we have to place the air conditioning system in such a way it's not producing a lot of noise, and also it is venting carbon dioxide properly. It should not affect the overall acoustics as well. So this becomes acoustics plus CFD problem. And this is regular office kind of simulation. If you have two options for air conditioner placement, where do you place, left or right, which gives you maximum placement? And if you take architecture inside this, people might want to place plants inside. When we think about CFD, we are not just looking at the thermal, but also we have to look at the aesthetics there, because some people might prefer keeping indoor plants, which is not good with fast moving air, right? So we have to place the plants in a recirculation region where the pressure is not so high and also the air movement is not so high. So it is mostly close to the air conditioner, and this kind of simulation is also there. And these are mostly our architects will be the customers for this kind of simulation. And then there is a fan optimization design. This is coming to design optimization. This can be merger of both aerospace as well as not aerospace, but mostly aero related simulation plus HVAC, because you have to look at the airflow as well as the design optimization for maximum airflow. So where do you place the fans? That's one kind of simulation, and how big your fan should be, or how optimized, or how much RPM is your fan is supposed to run to provide maximum airflow in a room that's not rectangular. If it's rectangular, we can easily say put it in the middle. But if it's not a rectangular room, if it's arbitrary, then how do you place your fan? These kind of simulations come in. And this is very good in OpenFOAM, because OpenFOAM has the sliding mesh motion simulations, like PimpleFoam offers that, and we can use these kind of simulation to do that. And I have done several simulations for this kind of application. It is really good. So if this is also an interesting field, because when you are doing a dynamic mesh motion simulation, you get both the both the scopes, like HVAC as well as aerospace, because if you're also working on propellers, it's going to come in handy. And talking about other different kind of scenarios where you will do HVAC, there is high-rise and urban microclimate studies, where your building is in scenario where the climate changes very fast, and how does your wind interact with the building? If you want to open your windows, it should not feel unpleasant, or it should not draw in a lot of dust. So your geographical placement is also very important, and LDS kind of simulation come in play here. And this also aids in natural ventilation. And if you are in a court, like a golf court or something, in those cases there will be a small area where people will be standing. And how do you place your golf area and your building in such way the air is not affecting the seating placement, right? So this is a kind of simulation which is not very popular in India, but it is there, so you have to know. And there is natural ventilation in buildings, and there is wind-driven cross ventilation. When you think about ventilation, we might think ceiling fans, air conditioners, but in countries like Germany, people prefer natural ventilation more than the air conditioner, at least for residential areas or very small offices, because there is a natural airflow. And how do we make use of that to our benefit to the maximum? And there is stack effect. So stack effect is like there is cold air in the bottom because of the heaviness of the air, and it slowly heats up. And if you're on a top part of a building, then it's slowly going to rise. And when you have your windows open, you're going to get hot air through your windows. It's very minimal, but it is an effect that is happening. And there is atrium, like if you have a balcony, how do you place your balcony? And do you really need a ventilation system in the balcony, or is your natural airflow enough? So these are luxury building kind of thing, but still it's necessary. And there is underground station. So this is very popular in Indian scenario, because we have a lot of subways, metros in those cases, and a lot of parkings in buildings. So smoke movement becomes very necessary. If there is unfortunately a fire, how fast can your fire be extinguished, and how fast can the smoke move? So fire extinguishers are there everywhere, but how fast can the smoke move? Because smoke is toxic. Even for the firefighters, it's going to be toxic. So how fast can you move it, and how do you place the ventilation system? How do you contain the fire? So there is a whole domain called FDS, fire dynamic simulation. So you can look that as well. And this is a very interesting domain, because if you are also from chemical background, you can see how do you extinguish using certain chemical and chemical reaction. This also comes under HVAC. And then again, the general large public spaces like auditoriums or stadiums, especially in malls, because the overall energy optimization is also important. Overall placement, like the design of the building itself, is very necessary. So as a CFD engineer, you'll be giving inputs to the architect or the civil engineer on whether this placement of air conditioner is good or not, whether it's going to provide maximum airflow throughout the building in a uniform setting or not. And this is a data center simulation image. So as you can see on the left, we have 4 racks and 2 plus 2. We can say it as 2 plus 2. Each rack is going to have a lot of servers, and these servers produce massive heat. So around 95 to 100 degrees Celsius of heat per processor. So we have two things. One is called the cold aisle and there is the hot aisle. And the hot aisle is between those 2 racks. So these hot aisles come in and because it's hot, it moves up. And the other side, we have the cold aisle where we place the air conditioners or pass in the chilled air. So because of the pressure gradients, it's going to take in the cold air, cool it slightly, and then the hot air moves up. After it moves up, we have to provide proper ventilation system or exhaust system so that the heat goes out evenly or properly. So even if it is very abrupt, we will not get proper airflow. It has to be very slow, and there is a thing called residence time. So even if your air is moving very fast, you're not going to transport a lot of heat, and it's just a lot of energy consumed in transportation of heat or the air. So we have to see whether the residence time is proper so that the convection takes some time, the air takes in proper amount of heat, the maximum amount of heat, and then it goes out so that the processor cools efficiently. So this is another kind of situation where we have to look at data and not just visualization. And if you take on the right side, we are looking at the streamlines. So on the hot aisle, we are looking at the streamlines and see how close should those racks be placed in order to avoid the flux from one rack to the other, because the heat of one rack should not go on and heat the other rack. So what should be the distance? Now it's again visual based more than just data based. So we have to look how many number of racks can we safely place inside a room. So this is another kind of visualization based simulation. And if you look at a 3D scenario, we have a whole lot of data centers and we have different placements and how do you put the vents, where do you place the door of the data hall, and how do you prevent the heat from going into the outside through the door, because there might be an office, we don't want the heat to exhaust there. Then how do you place an air curtain? So it becomes a whole lot of combination of simulations that I have told till now. And if you look at the other parts, let's say we looked at the broader picture like data centers and big halls, and if you look at a very small space like a office space, then we have to also see how this sunshine comes in. There is a lighting, because always we cannot place extra lighting. Sometimes people prefer natural lighting. And how many windows can you place in a wall? How much is it going to affect? Because radiation also comes in. Sun is going to heat up your room. And how much is your air condition going to work despite the heating from the AC? Sorry, heating from the sun. So these kind of simulation is gaining traction right now because people are getting conscious about getting enough sunlight and they want it even inside the room, but it should not affect the overall comfort inside the room. So we place both air conditioner and also keep translucent windows where we will get enough light from the sun. And this is a whole lot of different simulation, and it is going to be modeling internal temperatures. And then we have the radiative exchange between surfaces. Let's say you have two buildings very close, and one is having the outdoor unit of air conditioner here, and the other building has a window there. So this heat is going to affect it, not so much, but it's going to affect it anyways. You cannot open the windows. Then in those scenario, how do you actually place a sunshade, or how do you prevent the air from coming inside? How do you place the windows in such a way? So even if the building is already there, it's not like doing the simulation before the construction. Even if the windows are there already, how do you prevent? So you can keep an air conditioner or window AC near that, so you can prevent something. So this is very subjective, but it depends on the simulation, the scenario, and what kind of result are the customers expecting. But eventually, if you take the radiation apart from the heat from the motors and everything, it's going to affect and we have to prevent it. And if you take a building envelope design, we have to analyze the insulation. If you take a roof, nowadays people put weather cores on the roof so that the heat doesn't enter. But one step ahead, we can place solar panels on the roof, so we also get electricity and also avoid heat from entering through the roof. Because if you are on the top floor of a building, and if you try to put a ceiling fan, and if there is no weathering codes, you are essentially pulling the heat from the ceiling and you are pushing it onto the room. This is really bad. Even if the people inside the room want a proper air circulation apart from air conditioner, you are going to get like a more hot air than the cold air, because you're on a top floor. And how do you optimize that? How much weathering codes do you want to put? How much radiation do you want to reflect? So these kind of simulation is coming under the building envelope design. And we should also be looking at the glass buildings. If you are in a glass building, the radiation is going to affect a lot. So if you take some buildings in Chennai, you can see that there will be glass on the outside and there is a confined wall on the inside. The glass is just for decoration, because if you just keep glass windows, it's going to heat up further and it's not a good thing. So there is this kind of simulation where aesthetic comes into play more than just our comfort. And there is also seasonal or diurnal studies where the seasons affect how your windows placed. Because let's say in one season you are getting maximum airflow during the winter, so you want to prevent it because you don't want a very cold air. But in the summer you're going to get it very hot. So how do you manage? Do you place two windows, use it alternatively? This is not in a common household scenario, but when it comes to an office or high-rise buildings, this is going to matter a lot. So it's like this kind of scenario where there is a roof and it heats up due to radiation, and it should not affect how the building heats up. And finally, coming to the air quality and health oriented scenarios, where again now it is gaining a lot of traction. So after COVID, because in COVID we were advised not to use air conditioners. As I was saying already, air conditioners help in removing those pathogens. So why did we not use air conditioners, right? Because the air conditioner, before removing the pathogens, it creates a recirculation inside the room to collect everything and then push it out. But in a scenario like COVID-19, if one person is affected and if they disperse some pathogens onto the air, then the recirculation is actually going to make things worse and not better. So we have to be very careful in such kind of scenario, and not just in a scenario like COVID-19, even in clean rooms where we have to maintain certain pressure and temperature without any external air coming inside and infecting or creating any unnecessary air quality inside. So the clean rooms are going to be very specific on what quality of air you are going to get inside. So in those situations, we cannot use regular air conditioners, but we have to design it in a different way. So this depends on the customer and what they require from the building, and we have to design it in such way then we can use. Because if you take a regular CFD scenario like an air conditioner, we are just going to put a inlet patch and we will give the inlet, and it's going to create the temperature difference, is going to create the velocity. And then we will say, okay, this air conditioner is good, this is not, and this flow rate is good, this is not. But in a scenario where there is carbon dioxide buildup or there is a dispersion of particles, then we cannot just approach it in a regular way. And we would need a very fine mesh and big cloud computing like HPCs in order to do this kind of simulation. And because we have a compute capability now, this is gaining traction. Otherwise, the requirement was already always there, but now we have a lot of data centers and it is becoming accessible to a lot of people. So this is gaining more traction right now. And there is industrial workspace where, as I was saying, the FDS simulation, fire dynamics, the fume extraction and thermal plumes from the machinery, and how fast do you exhaust it, and how fast can you remove a contaminant without affecting the rest of the factory. So these kind of scenarios are very necessary, but as a consultant, we would not be getting this kind of simulation because it would be done internally in factories. But if you're aiming for a HVAC role in a factory, then if you have skills like this, it's going to really help. And there are special and emerging HVAC application like displacement ventilation system. So if you remember long back, we were having window AC. Apart from split AC, there is something called the window AC, where we place the AC right on the windows and not on the top. So the way split AC works is the cold air is heavier, so it is on the bottom, and hot air is on the top. And our split AC is going to cool the hot air, and the hot air comes down. The colder air becomes hotter because of our heat, the computers and the body heat, and it goes on the top. This continues as a cycle. But let's take a scenario where there is a small office inside a factory, and let's say there is a manager and he wants to get proper cooling inside his room, but it's not a confined room because it's a factory, right? So you cannot just put a split AC and expect proper cooling because it's not going to be circulating, it's just going to disperse. In those scenario, we have to place a window AC right next to his body. Then it is going to cool, and this cold air is getting hotter. It moves up, and then new cold air comes in. So this keeps happening. It is bit tricky to design, but it is very much necessary in recent scenarios because even in small places like a foundry, people expect proper comfort at least in cafeterias, right? So we have to do this kind of simulation, and there is energy optimization. As I was saying, now with a lot of IoTs, we can control how long is your AC running, how long do you want to keep your windows open. There are IoT based windows right now. So before coming inside your home, you can turn on your AC and then you can come inside to experience maximum cooling. And with the smart HVAC control, we can take the data and we can train an ML model, and we can see how often do they turn on their AC. This is for a specific person I'm talking. So these IoT devices will get optimized in such a way that they don't have to turn it on every day. If it sees a pattern, and if it also takes the outdoor temperature, indoor air quality, and based on that, it will turn on and turn off efficiently so that you won't feel very cold suddenly and we won't feel very hot. And the manual intervention of turning on and off becomes less, and in a way, it will optimize the energy. And because of recent advancement in machine learning and big data analysis, this is becoming a huge role in the market because it's not just for individual. Let's say you are a local seller and you are selling ACs, and if everybody is going to be around the same pattern, let's say the temperature is going to change the same for a lot of people in this locality, then you can deploy a model where it turns on and off based on the requirements as well as based on general pattern. So when you buy the AC itself, it is going to have some kind of behavior where it is kind of optimized, not to a specific need, but it will be optimized. So this is the kind of advancement we are recently getting with small devices which can be attached to existing ACs as well in your switch box directly. You don't have to spend a lot on buying new ACs for that. So there are IoT devices getting manufactured now. And coming to solar chimneys and passive cooling systems, there is a buoyancy driven natural flow, right? So if you take a chimney, it is going to push out the air. But where does the air go after that? It's going to affect. If you are in a very large apartments, you cannot just put all your chimneys right to the top and then let it out. And if there is someone on the top and they also connect it to the same exhaust, it's going to get very clumsy. In such scenario, how do you passively cool it? Like, can you pass it through a lot of copper tubes, cool it passively through the external air, and then push it out so that we are not contributing to a lot of global warming? So these kind of things are gaining traction in manufacturing, but even if it is just manufacturing, we have to do the CFD in order to make it optimized. So this is slowly growing, not very much popular in India, I would say, but it is slowly gaining market. And there is radiant panels and floor heating system. As I was saying, we can place solar panels on the roof so that we can avoid heating on the roof, which will eventually heat the building. But if you place radiant panels, if you are not going to spend so much on your solar panels, if it's not within your budget, or if so many solar panels are not necessary for your building, then how do you use? Then we can use radiant panels and floor heating systems. If it is a colder area like Germany or Switzerland, then you can have a heating system instead of a cooling system. And this is like a advancement in OpenFOAM. This is by Professor Blockend. It's called Wind Driven Drain. It's an external library. You can just search for Wind Driven Drain OpenFOAM GitHub. You'll get a repository. You can compile it within OpenFOAM, and you can see how wind is going to affect the rain patterns. So how do you optimize your windows? Or if there is a wind shear blind in a building, then how do you place it? Can you close it automatically when there is a rain? How much do you close without making the inside room hot? Because the outside is going to get very humid and eventually it gets hotter inside. Then how do you prevent it? So this kind of simulation has been done recently. And our latest kind of, I would say, simulation is solar radiation. So this is done in open form, but I have not seen a lot of people doing it. So it's like you have windows, you have a room. If you have opaque or translucent windows, then it's going to behave differently. When you have a transparent window, it is going to behave differently. The radiation due to sun will affect your room. And there are models inside OpenFOAM where you can give the entire path of your sun with latitude, longitude of your location, and you can see how much of heat you are going to get in a specific day. So if you have those data, you can place your sun, you can model your sun in a specific location, and you can see how much of light is going to come through your windows. It's going to serve in two scenarios. One is like how much lighting are you getting? Second, how much radiation heat are you going to get inside your room? In office setting, this is going to affect a lot because as I was saying, when you do radiation analysis, apart from the natural lighting, you also get heating. And how do you cool it actively using your air conditioners? So now this is slowly growing field, I would say. This is done both for internal as well as external, because if you are having a huge wall which is restricting the light, or another building that is restricting light to your building, then how do you actually optimize through reflective panels to make more natural lighting into your room? So these kind of simulations are being done, and this is like a small example. You can see I have placed a block on the right side, and it is affecting how much of the radiation is passed through because it is taking in some radiation, and you can see the shadows there. And unfortunately, I was not able to put the actual numbers here because of confidentiality, but what you're looking there is temperature contour. The left is without any blockage, right is with blockage with more sun. And this is another interesting room design where we have a lot of windows we can see, and we can specifically see the patterns of how the sunlight is affecting inside the room. And if you closely look at the table, when the sun is coming through the windows, the table has a blockage which is affecting, or let's say preventing, the light from going to the other person's, let's say, computer. So how is this useful? If you have a natural lighting in a room and you have a lot of monitors, monitors are not going to like the sunlight. So how do you place your monitors, or how do you restrict the light from directly hitting your monitors or projectors? So this is something which we have done recently, and it has been successful. And finally, we have shadow casting. So this is not based on OpenFOAM, but this is also part of HVAC. I personally love this kind of simulation. This can be done in two ways. One is you can use animation software like Blender and use ray tracing within that. So there are models like Cycles, EV. EV is not good. Cycles is, I would say, is good. So you can have a light source, let's say sun, and you can give specific wattage like 700 watts or 800 watts, and you can see how much of light are you getting inside your room. So this is more like shadow casting. And can you put more shadows? Can you get more lighting? So this kind of designs can be optimized in software, even an open source software like Blender. Or if you want to go further, there is a library from NVIDIA called Iray. So you can use Iray software to do this kind of simulation. And this has been gaining more attraction in the recent times because of the ray tracing, GPU capabilities, and a lot of rendering. Because when you show it to the customers, if you show along with the shadows, it's going to be more attractive. And this can be done for even large buildings without having much of overhead because it's ray tracing and it's done on the GPUs. So you can massively scale them on GPUs. I have personally done this only on NVIDIA GPUs. I'm not sure about other ones, but NVIDIA GPUs are really, really capable of this, especially along with Blender. If you are going to use it, use Cycles library, and it will be a very interesting scenario, even if you are not totally interested in HVAC. But if you are interested in kind of rendering and animation, you can look at this, and it's going to be very interesting. And use of OpenFOAM in HVAC. So this will be my covering of how do we use OpenFOAM in Codedynamics for HVAC. So mostly we are just dependent on 5 different solvers. One is buoyant simple foam. When you have heat transfer along with steady state, then we use buoyant simple foam. But if you want a transient analysis, we go for buoyant pimple foam. And if there is no heat transfer, but you just want to see the overall airflow without any heat transfer, then to make model simple, of course, there is heat transfer involved, but if you want to just model it simply, then you can use simple foam or pimple foam for steady and transient analysis. I think you will get hold of simple foam or pimple foam by the end of these workshops, because you'll get hands-on tutorials. And there is CHT multi-region foam. So this is the scenario where we have radiation, right? So we have to choose the thickness of the glass or the tent sheets. And if there is an electronic cooling and you want to put heat exchangers. So when I mean electronic, it's not like a small CPU, it's like whole data center where we have conjugate heat transfers. So CHT multi-region foam is a very good tool, and we do a lot of simulations using CHT. And combined with CHT, we also use multi-phase solvers to do like, let's say, oil dipped processor cooling in a very big HPC. Some people prefer to put it in a mineral oil so that they can cool it actively. It's not recommended, but people do it. So uh, how much of the cabin size do you need to actively cool the processors, the entire electronic components? So these kind of simulation are done in CHT multi-region foam, and open foam is never short of any capability when it comes to HVAC, because even the radiation and light casting, which I showed you, was done in open foam, and without any other external tool, mostly you can do just open foam simulations, and you can get very good results. And along with some capabilities of ParaView and Blender, you can take it further to do the ray casting and shadow simulations. So this is one interesting simulation that we did. It's like what, 8 fans, and all 8 are rotating. And how do we get the patterns inside? It's not an ideal scenario where we will actually put this to use, but we just wanted to test the capability of open foam and how much can it handle, because all 8 are moving, and we are going to get a lot of velocity fluxes and pressure gradients. So this is a confined room. There is no inlet outlet, just fans rotating. And it was a great success. I wish I could show the video, but unfortunately I can't. So, and this is the 3D view of it. So we can see how good the overall simulation looks like. And another use case is actively chilled beam and actively chilled beam plus ceiling fan. So as I was saying, ceiling fans really help even if you have air conditioners. You can see how much of velocity movement you get, and which is going to affect the thermal movements as well. So we get more comfort. And this is like a planar view. Again, the same scenario. Left is actively chilled beam only, right is actively chilled beam plus a ceiling fan. And I would like to introduce you to a very small product of us. It's a work in progress. It's called the bladeless exhaust fan. And the inspiration for this product is a product called Air Multiplier from the well-known manufacturer Dyson. So we took inspiration from the Air Multiplier product, and we have made a bladeless exhaust fan, which has a lot of benefits like less noise, aesthetically pleasing, very easy to clean, and safer than an exhaust fan just exposed out there. And the current status is we hold the design patent of it. We have technology readiness level about 4. We have a prototype, we have demonstrated it, and we are in a funding phase. So we hold the design patent for it, applied for product patent, and we'll be getting that soon as well, I hope. And the project scope is we have to optimize the design in the first place, because we know the product is working, the hypothesis is working, but how much can we optimize the exhaust behavior so that we can put it to actual use in a scenario where there is a household kitchen, or if there is a restaurant where aesthetics matter more than household. So instead of just a noisy, uh, bad looking or ugly looking exhaust fan, we can place something like this, and it will be more optimally performing as well as aesthetically pleasing. That's our idea. And we are just working on the design optimization. So the overall idea here is, if you take a cross section of the circular thing which is shown here, it will look like an airfoil. And this is essentially an airfoil, but in a modified way. So you pass in air using a impeller, and this passes through the small airfoil inside of the airfoil, and there is a small slit. So this slit is going to push through the air, and because of the viscosity of air, it is going to try to stick to the wall. And when it moves out of the airfoil situation, it is going to create Coanda effect. So because of Coanda effect, on the right side, you are going to get a low pressure. On the left side, which is the inside of the room, I would say, is going to have high pressure. And because of this, the air is going to move from left to right, which is the inside to out. So as you can see in this image, it is just going to move from left to right. And apart from just the inside of the circular thing that you are seeing, it is also going to take the air outside it because of the viscosity of air, and it's just going to draw in a lot of air outside. So if you are in a kitchen and if you have just a hole for exhaust fan, that's not going to be useful for this product. But if you have a window and if you just place it there, it is going to take a whole lot of air and pass it through the whole window instead of just a small slit. And based on simulations, we prove that it is much better than the regular exhaust fans in all kind of scenario. And these images are not from our product due to confidentiality. This is from uh, papers and websites that demonstrate how Dyson fan actually works. And what is the design optimization scope that we are looking here? So one is there is an impeller that is working inside the product, because without any movement we cannot get airflow. So there is a duct. Inside the duct we have an impeller. And originally in the Dyson fan, it is optimized for airflow, which is the push of air bit, but we are optimizing the airflow design as well as the impeller design to provide maximum suction. So because it's a suction, it's not going to rotate the same RPM all the time. It's going to oscillate between certain RPMs, and it is kind of not an ideal scenario. So I don't want to disclose a lot here. So the impeller is there. That's the ideal scenario. And we are going to get maximum suction in the high pressure region, and it is going to push. So the overall idea is we have to create a big low pressure region so that the exhaust works properly. So what are the optimization? We have to optimize the air entrainment, how big your hole should be, like the diameter of the fan, how big should it be, and for what kind of scenario. If it's a kitchen, it could be small. If it's a restaurant, it could be big. So how much do you want to put it? And what should be the slit thickness, and what should be the lip geometry? So the slit actually matters because it is creating Coanda effect, and how do you optimize to provide maximum airflow and without the flow separation, so that it sticks maximum and it provides more effect. And we also have to minimize the drag. And why do we have to minimize the drag? Because it is going to hang in just a duct, and if it is going to have a lot of air movement, eventually this hinge can become weak, which we actually experienced, and we don't want that to happen. So it has to move, and move without a drag. That is one part. But the other part, because of drag, there can be noise. So the overall idea of this fan is to reduce the noise. We are working on acoustics, but if there is going to be drag when it moves, it is going to create some noise, which we don't want. We are just going to optimize that. And it also provides like full surface guidance. It's like it should also look aesthetically pleasing. Just because we are going to optimize the airfoil, it should not look very curvy, and it should not become very hard to clean. It should not become very flumpy is what I mean. So it should be able to handle stress properly, because when you clean it, if you put load on it, it should work fine. So these are the kind of optimizations that we are looking at. And just a final note, for some simulations, we partner with a company called Tian Building Simulation. It's a German company. They have a tool called BIM, which is for Building Information Management, HVAC tool. It is an OpenFOAM based CFD tool. It has a GUI, and it can perform a lot of simulations related to HVAC and fire, and also shadow casting. And they have been in the market for a very long time, and this is how the software interface looks. And this is one of the biggest projects that they have done till now. And I'm glad that we have been sponsored by them for some of our simulations with their software. And if you are interested in buying a software or exploring the software, you can contact me and we can look through that. And finally, yeah, this is my contact details. If you want to contact me for any suggestions related to HVAC design, or if you have any questions like as a student, you can still ask, because as you might know, we take classes for OpenFOAM. And I mean, there are a lot of open source free resources available. And if there is something that you are not able to get through the free resources, then of course you can contact us. And if you have any questions, please ask now.
Thank you, sir. If anyone is having question, they can just post their questions in the chat box or can unmute themselves and have a chat with Mr. Harish.
We have a question in the chat box.
What are your thoughts on skin texturing of airfoils? Actually, we tried one. There is something called the chevron corrugation. I think if this is related to what you're asking, then chevron corrugation actually helped us in the texturing of airfoil in noise reduction, basically. So it creates very local small recirculations, which helps us in uh, preventing airflow separation as well, and also on noise reduction. So apart from that, we are not aware of any skin texturing for airfoils. Did that answer your question? No? Okay. How to select an exhaust fan based on inlet fans in cooling? So inlet fans, do you mean like a ceiling fan which is placed in the room or something different? Okay. So in general HVAC simulation, there is a big problem, which is like even if you have any kind of electronic cooling. So if you have a cooling, let's say an air conditioner, in a regular scenario, what you might assume is every door is closed, every window is closed, you have an air conditioner and you are just passing in. But the problem in HVAC CFD simulation is that because of the continuity equation, we have to conserve the mass, and whatever is coming in, it has to go out. So we artificially place an outlet and it has to be moved out, even though it is not the regular setting in a building. We have to place it. But in a regular way, what happens is there will be minor leakages under your door and windows. So coming to your question, if there is an electronic cooling and there is an exhaust fan, first you have to run the simulation without an exhaust fan and see what is the maximum outflow that you are getting naturally when there is a cooling, like an air conditioner, or if there is a chiller. Then because of the pressure difference, how much of exhaust are you getting naturally? Then you have to take that into account, and what is the uh, whole size that you can place. So that is one thing. And if you can finalize on the diameter, then you can go for standardized exhaust fans and you can see what is the speeds available. So the thing with exhaust fans is that you cannot control the speeds, unlike the ceiling fans. So you have to look at the diameter and the speed, and you have to see the mass flow. So most of the manufacturers give the mass flow rate, and you might know what would be your electronic cooling mass flow inlet. Then in that case, you can just choose based on the standardized exhaust fan. So first, the step will be like do a simulation without exhaust fan, see what is the maximum velocity you're getting or mass flow, then see how much of exhaust do you really need, the mass flow, then look for a manufacturer that gives that mass flow, and then you choose the diameter of hole based on that. I hope that answers. Okay. Related to this, government run hospitals, yes, CFD can help to improve the facilities, but the other problem is the scenario where they are going to place the air conditioners, like the circulation or ventilation. It has to be constructed in such way. So if there is a already constructed hospital, then it might need a bit of rework because it might not have the proper construction already done. But if you really want to optimize, then you can actually do it to certain level, maybe not totally, but it is possible if there is enough funding, and there is a scenario where the building can be altered a bit, then sure, CFD can definitely help. Any other questions? dew point evaporative cooling. So it is possible in CFD, but personally, I have not worked on it. Never got the chance to work on it. But it is possible in OpenFOAM as well. So you just have to add a scalar. You don't need a multi-phase solver. You can use your regular solver, and you can add a scalar to it. And you might need a bit of modification to the solver, and you can do it. But if you are looking at the evaporative cooling as such, then you can use um, phase change related solvers, and it is possible. I have not worked on phase change related to HVAC directly. Sorry.
So Harish, I have something to tell you.
Yes. Yeah.
Like majority of the participants who have joined today are students, and
Okay.
they might be interested in applying for the FOSSI internships and fellowships. So could you
Okay.
please kindly share your experience as an intern,
Yeah.
or give them some tips so that they can, easily clear the screening tasks and they can do a very good project in case study or research migration?
Yeah, sure. Okay. So first I'll start with my experience with FOSSI. So I joined FOSSI, I think around 2.5 to 3 years back as a summer fellow. And when I joined, I only knew how to follow a YouTube tutorial. To be very honest, I had theoretical understanding of CFD, but I did not know a lot about OpenFOAM, but somehow I made through. And the kind of support I got at Fuzzy was very, very good. And whatever I learned after that with OpenFOAM and in CFD in general, I I would give a very major portion of the credits to Fuzzy because I got really good mentors, and Fuzzy is very, very supportive. This was my experience. And the other part was I was actually an online intern. I was not able to come to the campus in person, but still I got very good support, and I got the time, even though there was a time constraint. My Professor Dheeraj Garg, and my guide was, I think, Mr. Abhushan Regmi. So they both were very helpful, and the kind of support I received throughout the fellowship actually carried forward. And that kind of inspired me to work further on OpenFOAM. And after 3, 4 months, I applied back as a research assistant at Fuzzy itself, and I worked for around 5 to 6 months. In that scenario, I worked on a lot of case studies, upgrading case studies from one version of OpenFOAM to other, and I also worked on workshops like this. So the last workshop, I was on the other side. I was actually giving demonstrations. So in those setting, we actually work with other PhD people who are working in FOSSI, the other masters and research students. So we get the kind of exposure that you will not be getting anywhere else. And you also get good guidance and up to dates and updates from Pile. And it was very kind of happy and inspiring. I never thought like, oh my God, I should work today. It was very exciting, I would say. So you should definitely apply. And regarding the screening tasks, mostly the kind of task that they give is very easy. And the thing is, the screening task, you can follow any standard textbook or tutorials and you will be able to make through. But the way you put your result and the report actually matters, because a lot of tutorials are available, including my channel. Some of the screening tasks are available after they are, of course. I would say it is removed from the screen task list. I would also update it as my video. But the way you put it in the report shows the understanding that you have on the fundamental physics that is happening there. So apart from your CFD and OpenFOAM knowledge, I think Fuzzy would value the kind of understanding and approach you have towards the problem. So I would say focus on your fundamentals of fluid mechanics and heat transfer, and then you do the CFD. So even if there are minor flaws, you can come here and of course learn a lot, and it will carry forward for the rest of your life. And the kind of teaching and the support I received in Fuzzy is what inspired me to start Codynamics as a YouTube channel, and I started putting a lot of free videos out there, and it has been successful for the past 3 years, I would say. Yeah, ever since I joined Fuzzy, and I received all the support and guidance. I mean, not guidance. I was able to guide a lot of students only because of the kind of inspiration I got from Fuzzy. So I definitely recommend everyone of the participants, if you're a student, apply to it. Just give your shot, and if you are selected, then it's going to change your life. It changed mine. I hope it will change yours. Yeah.
Thanks a lot. Thanks, Harish.
Mm.
So I hope, yes,
One
so at
more
the
question
end of the
is
workshop,
there.
yes, one more question is there. So at the end of the workshop, I'll elaborate about the internships and fellowships. I didn't talk about that in the introduction talk.
Okay.
Uh, so thanks a lot for sharing your experience. It was
Okay.
very useful because see, people actually think that it's IIT Bombay thing, so it is a very tough job and all. But we are really focused on, nurturing the talent or the skills that the students already have and to develop them further. And
Yes, definitely.
yeah, and that's what FOSSI is meant for, and that's why the government of India is funding FOSSI so that we can raise the mediocre students of India so that they can perform well in their career. They can come up with startups. They can join the education industry or MNCs.
Yeah, definitely.
So yeah, yes, you can take up the question. There are I think two more new questions are there.
So there is a minimum air change requirement in pharmaceutical sector. Can CFD help to reduce the air changes and save energy? Yes, it can definitely help. And the air changes when you mean, so as I was saying for the previous question, regardless of whether you want or not, you have to place an outlet. So I'm not very sure about the air change because anyways you have to push your existing air outside. But if it is just internal circulation, there is no inlet like an air conditioner, just fans, then maybe it will be helpful. But I'm not very sure about the air change. And for saving energy, yes, it will definitely help because you can optimize the placement of your air conditioner and the amount of airflow. As you might know, the requirements of the temperature is different from what you would see in a regular household or office. So for that kind of temperature, how how do you turn on and off the air conditioner with a smart setting? You can simulate the entire thing over hours and see how often can you turn on and off. This is one kind of saving energy. The other kind, the placement itself plays a major role in how long does your air circulation sustains the temperature. This is second. And the third is kind of the conjugate heat transfer kind of simulation where you can put specific paints that are available nowadays for pharmaceutical applications where there is a maximum insulation of the air movement. It does not go inside the concrete and cause the carbon dioxide buildup. So you can do these kind of simulation as well if you are good with chemical reactions. But in general, yes, it can massively help in saving energy. And so how can we set the heat transfer coefficient for transient and non-uniform heat transfer simulation in answers flight outcome? So this is not something that I can actually answer without a proper mathematical presentation. I think when you are looking through the hands-on tutorials, I think you will get this clarified. But in general, what I would say is we cannot just set the heat transfer coefficient right out of the bat. So it depends on the geometry, it depends on the uh, kind of simulation that you're doing, kind of material that you're using. So at least in HVAC, the material matters a lot. So heat transfer coefficient, I cannot just answer simply. Really sorry about that. Yeah. So I think that's it now.
Yes, I was thinking that they don't have any more questions.
Yeah.
So even if the participants has any more question, they can directly contact you or they can contact through us.
Yeah, sure.
Yeah. So thanks a lot for the excellent session, Harish. So
Okay. Thank you.
yeah. Okay. Please stay connected.
Yeah, sure.
Yeah. Okay. Yeah. Okay. Thanks a lot. Bye bye.
Yeah, thank
So
you.
we can thanks. So we can move ahead with the demonstration session now. So team members Paris and Evan is here. They'll carry on the session.
Yes, ma'am. So, good afternoon, everyone. I hope you enjoyed Harish sir's session. Uh, Before moving ahead, so like today we'll be demonstrating airflow and ventilation case study only. So just a minute, I'll share my screen. So is it visible? I hope it should be.
Yes,
Paresh, just increase the size.
Huh. Okay. So, okay. Let us try the. Okay. The screen is visible, right?
Yes.
Yes. So, good afternoon to every CFD enthusiast who are present. My name is Parish Palkar, and I'm working as a research assistant at FOSSI CFD team in IIT Bombay. And this case study demonstration is a part of the industry readiness workshop. And as Harish sir has very beautifully explained about airflow and ventilation analysis, we are also going to demonstrate and see how we can also um uh, make our own airflow and ventilation analysis in open form. So again, this is the open forum. I would just like to thank Dr. Kannan, Chandan sir, and Payal ma'am for initiating these such events, and we are really grateful for them because of them we are having these events. So as Harish sir has explained, what is HVAC? So HVAC stands for heating, ventilation, and air conditioning, and air ventilation has a very crucial role in maintaining the air door quality, thermal comfort, and occupant health. And the simulation in the HVAC domains are carried out for buildings, in a means internal domain of vehicles, let's say aircraft or car, and industrial facilities, for example, plume dispersion or something like that. And these simulation helps us optimize the design that we are intending to develop, and start the production. So simulations of heat transfer helps us to optimize the design in a better way, rather than just solely depending on the CAD models. So there are general steps that are carried out in a CFD simulation. So in any CFD simulation, this is just not bounded to the R case, but in any simulation, there are four parameters. First is pre-processing, second is solver setup, third is monitoring and solving, and third is post-processing, in which results and interpretation falls. So let us look at them one by one. So the first thing is the geometry creation. So in pre-processing, there are three domains. First is your geometry creation. So geometry you can create using any external CAD modeling software, like FreeCAD or SolidWorks. Even you can use CATIA as well for that. Meshing, same, for meshing you can use block mesh and snappy X mesh. We have had the tutorial for the same in the morning session. And the boundary location, so it is a part of meshing itself. So, and we have to identify which is the boundary patch, and segregation of domains of your CAD model. So these three things are done in your pre-processing. Then we move forward to the solver setup. So solver selection is a very important parameter while setting up any case. Means you have to first identify what you want to simulate. Is it steady state? Is it transient state? Or is it going to implement the density based changes? Or is there something related to compressible flows? So OpenFOAM has a vast category and catalog of solvers. So you have to necessarily choose the ideal solver that is fulfilling your need. And then process, model, and method. So as we solve the Navier-Stokes equation in the solving part, we have to appropriately choose the schemes that are required to solve the particular equation, and same as numerical method setup. And then we go to solving. So in solving, we generally run our simulation, define at for how much time we are going to simulate our simulation. Uh, we also, if it is a transient simulation, we have to also carefully monitor the time step. As if we give very high time step value, the simulation will definitely crash. And the current criteria is basically the current number. Current number is used in transient analysis, So we have to specify Coran number as well in your control dictionary, and it is just Coran number is just an way of information that is traveling to your particular cell. And then we go to post processing and results interpretation. So in that we analyze flow patterns, we visualize velocity and pressure contours that are occurring. If we are working in HVAC domain, so we also visualize the temperature gradient and is are there any recirculation zones, or if we find like if we are doing an airflow analysis, if we found out there is a dead zone occurring, so we have to optimize the design as well. So we can do that as well just by post processing the data that you have simulated, provided you have done all the three things correctly. If you have fumbled in applying any means appropriate solver, so it is expected that you won't get the results that you are expecting. It is not working. Wait. Okay, so this case study, it is you can go on fossicfd.in. I'll show you. In the case study, once you go on CFD Fossi Home, you can go on case study project, and here you can find the completed case studies. And in that, the case study that we are going to demonstrate today is the case number 150. So this is the study of airflow and impact of exhaust, window AC and split AC on air ventilation in the MFST room at IIT Bombay. So it is a real-time simulation that has been carried out by Mr. Akhilesh Pongshe. He was an MTech student under Janani ma'am at IIT Bombay itself. So when they have done some simulations, and we are going to see it. Also, just if anyone who does not have any idea about the how to download the codes, either you can download the abstract only and check what is occurring in this simulation, or you can download the entire case study and reproduce the results yourself. So let us go on the presentation again. So the title of the presentation is the study of airflow and impact of exhaust on window AC and split AC on air ventilation system in MFST room at IIT Bombay. As I said, the author is Mr. Akhilesh. He was an MTech student at IIT Bombay. And how you can navigate to this study, once you go on cfdfossey.in, in home, go to the case study project, and in that completed case study, and you can find the case study number 150. So you can download either the abstract or you can download the full codes from the website. And the versions that we are using is OpenFOAM 9. It is the foundation version provided by openfoam.org. So we have there are certain objectives that are being set to demonstrate this case study. So first objective is to understand the significance of air changes per hour to manage the indoor quality. The second objective is to check how adequate ventilation and how to reduce the risk of disease transmission and comfort analysis. Third is this is more about the implementation part. So approximately 25 simulations were carried out by fixing the exhaust position, and the only changing parameter was the horizontal position of the exhaust. And the main interest was to find the air residence at two different heights, that is 1.3 meter and 1.6 meter respectively. So moving further, let us have a discussion on the geometry. So if you are able to see my mouse, this is the indoor door. It will be working as the fluid inlet. The dimensions of the door are 0.8 meter into 1.9 meter. We have attached an AC air conditioning system here that is 2 meters above from the wall, and the dimension of the AC are 1 meter in the horizontal length and 0.3 meter in the vertical. And we have also attached an exhaust in the front wall that is 3 meters above from the front wall. and the dimension of the exhaust are 0.5 meter into 0.5 meter. And the modular that in which this geometry has been created is ANSYS space crane. So it is one of the utility in ANSYS for creating your body. So this is the total this is the way you can visualize the mesh as it has been made in ANSYS. This is the ANSYS mesh, and this mesh is once we have converted the ANSYS mesh into OpenFOAM mesh. So here you can see there are two exhausts in the ANSYS mesh. One is here and second is here. So parametric study was conducted to check which produces better air resistance residence, single exhaust or dual exhaust. So simulations were carried out for both. This is the AC. You can visualize it here as well, and this is working as the inlet fluid, and you can see it here. And the mesh details are the total cell count is around 1.6 million, and all cells are hexahedral. The skewness is 0.041, which is okay. And what the maximum aspect ratio that the mesh is going is 1.72. So before moving further, we have to make some assumptions. That first thing is the fluid that we are simulating is air, and the air is assumed to be incompressible and ideal gas. So here we are going to implement the K epsilon turbulence model. There are multiple versions of turbulence you can implement, say K omega, K epsilon, laminar, or there are various ones. We can explore that later, but you can implement various turbulence model, and one of which they have implemented is K epsilon. So we have to calculate some numbers to put them into the zero dictionary to carry out our simulation. So we need the values of K, that stands for turbulent kinetic energy. We need turbulent intensity, that stands for I. We need turbulent dissipation rate, that is epsilon, and we have calculated the Reynolds number. Okay, so going first, let us see how Reynolds number is calculated. The Reynolds number is given by density into free stream velocity into your characteristic length upon the viscosity. So that comes out around 13,200. So if you can see, one is the indoor patch that is working as a fluid inlet, and also the AC patch that is also working as the fluid inlet. They have calculated Reynolds number for both, but as the Reynolds number for AC came out to be 12,000 and the Reynolds number for the door came out to be 13,200, so we are going with the higher Reynolds number. After the Reynolds number is calculated, our aim is to calculate the turbulent kinetic energy. But again, for turbulent kinetic energy, we need the turbulent intensity. So the turbulent intensity is given by 0.16 into Reynolds number to the power minus 0.15. That came out to be 0.0487. Once this turbulence intensity is calculated, we put this into the first equation, that is of turbulent kinetic energy. So it is given by, it is K, it is given by 3/2 into free stream velocity into your turbulence intensity, and which came out to be 9.735 into 10 to the power minus 5. And once K is done, our next step is to calculate the epsilon. So the epsilon is given by Cu. It is also known as the empirical constant to the power 3/4 into your turbulent kinetic energy to the power 1.5 divided by 0.07 into the characteristic length. So here our characteristic length is in horizontal, but if in case there is any internal flow, you can consider it as your diameter as well. So the epsilon value came out to be 2.8 into 10 to the power minus 6. So now let us check boundary condition files in detail. So this is our case structure, if you can see. So this is the zeroth file. So the zeroth file contains all the necessary information regarding the initial and boundary conditions, along with the turbulence property that we are intending to implement. And also the AC inlet flow rate was taken as 350 cubic feet per minute, and the exhaust flow rate was considered to be 26 meter cube per minute. Once you download this case study now, there are detailed calculation how this particular value was selected, but due to time constraint I am skipping it. But if you download a whole case study, there is a detailed description how all these values were calculated. Okay. Now coming to the constant folders contains two main parameters. First is transport properties, where we basically tell the OpenFOAM that which fluid are we using? Are we using air or water, or is there any other fluid? And in the turbulence properties, we specify the turbulence model that we are intending to express. And here in this case, we have selected the K epsilon turbulence model. Also, as we have seen in the morning's session, this folder also contains folders like try surface, which contains your STL files, a polymesh folder. Once your mesh is generated, OpenFOAM will create a polymesh folder that will be kept inside your constant folder. That contains necessary information regarding the your mesh. And there are also some other parameters, like if you want some dynamic meshing or something, so you can add that as well in the constant folder. And now coming to the system folder. So the system folder consists of the information regarding your simulation. We'll look into it in detail, but just to briefly tell you that what are the internal and external parameters that we are considering. In control dictionary, you can specify what are the things that you are expecting from your simulation, and there is a decompose predict as well. So this decompose predict will help us decompose our case, as we have seen in the morning session while running our simulation on parallel. So to run your simulation on parallel, firstly we have to decompose this particular case into subdomains, and then we have to mesh it, and we can solve our uh, uh, simulation on the uh, decomposed domain. Okay, so before going to the art form and custom solver, let me take you to my terminal. Let me clear. Okay, is my screen visible? Can anyone just confirm?
Yes, Paris.
Okay. So before going that, let me go to my home directory. As again, I have set an alias to navigate to my OpenFOAM 9 folder. So I'll just type OF9, and it will prompt a message that foundation version has been sourced, on which the simulations were carried out. So I'll go to the run folder of OpenFOAM. As I said, the OpenFOAM run folder is located in the OpenFOAM, and you will have your particular name. If you are having OpenFOAM 2412, so it will be defined as your name, and in hyphen in front of the version of OpenFOAM. Here in this case, it is my name hyphen the OpenFOAM foundation version, that is 9. So I will list out all the contents that are there. So here there are some files. We'll just go in the necessary ones that we are interested. Okay. So there are two cases. I'll go in the 3. Okay. I'll explain you this case in detail. So if you, okay, I have to now I hope the screen must be visible now.
Yes, Paris.
Okay, so once you download the whole case study from this domain, once you unzip it, you will get all these necessary files. So let us go one by one and open the readme file here. So it is already open. Okay, so there are some steps that are given. Okay, download the ART form folder and save it. So we will start from the scratch. So here they have basically said ki we are going to simulate air residence time in MFST room at IIT Bombay. And here we are going to use simple form, which is a steady state solver. And for that steady state solver, we are going to implement the K epsilon model for flow velocity and simulation. And we are going to use ART form to calculate the air residence time simulation to successfully run the simulation. You can follow these steps. So first step is so basically they are telling us how we can run the whole simulation. It is a very nice way to understand what you are going to do if you are new to OpenFOAM, or let's say you don't know anything about a particular case study. So at FOSSEE, we generally follow rule to whenever we are publishing a case study or research project or lab migration, we put a README file so that the user who is new to a particular domain can read the README file and he can start simulating it. So there are some necessary conditions that are used key if you want to compile the solver, how you can do it, and to calculate the air residence, how you can do, and how you can run the simple form solver. So let us go in the common case first, and in the velocity folder, as they have said, go to your terminal in the run folder and please download the case file called velocity and save it into your run folder in your OpenFOAM. So as I have extracted the whole case study in my run folder, so it won't be an issue. And then by using the command cd, that helps us to go into a particular folder. They are asking us to go in the velocity folder and then type bash, all run there in the terminal. And after completing the successful simulation process, we can visualize the results using Parafoam. So let us go in the velocity folder. So I have already ran this case. I'll just explain what are the boundary conditions and everything that is present. Let me open this. Okay, so we can start from the scratch. So here it is the form file, and it is the vector field. So you can pay attention to this, that if we are talking about a scalar field or a vector field, so if there is a vector field written, so we are particularly discussing about the vectors. Again, the dimensions are the dimensions that are given to the particular folder. Here as we are discussing with we're dealing with velocity, so the second column stands for meters and the third column stands for time. So the velocity will eventually come out to be meters per second. I'll just convert this to C++. Yes, so the SI unit of this particular field will come out to be meters per second, and we have internal field uniform 000. As internal field are some dumped values that we can place in our simulation. It is similar to the ANSYS initializations if anyone has used ANSYS. So this is it. And then we will go to the boundary field where we have defined all of our patches. So first is the inlet. In inlet, we have given the fixed value. So the door will work as the inlet, fluid inlet, velocity inlet, and in the negative z direction, we are giving a velocity of minus 0.165 meter per second. So in the presentation, I told you about that the velocity that we are giving to the solver. Just a minute. So the velocity at the AC inlet flow was taken 350 cubic feet, but here I am writing this, the values are different. So it is because the calculations in the report were done considering cubic feet, and here we are considering meters per second. Okay. Then coming to the outlet, we have specified pressure outlet, zero gradient. The AC is fixed value again, uniform, and we have calculated, we are going to provide the velocity in the x direction as well and in the y direction as well only in the negative x direction. Once we start visualizing the content, we would be able to see it in a very good, better way. But we will visualize them after some time, because or else the paraview might look very bit clumsy. And then we are going to the wall. So there were multiple walls that were present. Here you can see. So the wall patches have been kept as no slip. Uh, we can open the next pressure folder again. So as I have explained you, this is the pressure, this is the scalar field, these are the dimension of the pressure, and the internal field here is also 0. For inlet we are giving 0 gradient, and at outlet we are conforming it with a fixed value called with 0. Okay, and the wall is also 0 gradient and AC is also 0 gradient. So in open form, if you want to write any parameter that are having same boundary type condition, you can write in this way as well. Or if you want, what you can do is, let me comment this out first. What you can do is double comma, we can type like this, and we want our AC, and the AC should be in this format. I'll switch to C++. So now without using or utilizing much space, we have given the type 0 gradient to both wall and AC. That was taking much time. These are some basic uh, uh, how do I tell you, some basic uh, tricks or tips that you should know if you are implementing same type of boundary condition. Also we can use this same approach for inlet as well. Okay, but now for being let us keep the way it was. Okay, so the pressure field is okay. Now let us go to the key. As we have calculated the K, so we are just fixing it with the inlet parameter of turbulent intensity kinetic energy inlet. So this is a special type of inlet where you can fix the value, and we can give the value internal field, which is uniform, which is this value. Again for AC we are giving the same field. So as I told in the pressure parameter, we can combine or we can club two patches in a single line using the commands. You can do that for uh, these patches as well. So let us say this is outlet, it is set as 0 gradient, and there is wall, and the wall is given the R wall function, and the value is the internal field uniform, that is this value. It is specified previously only. And the AC and inlet values, intensity values, we have calculated it. You can see it here. These are the same values that we have implemented here. We could have given the R wall functions and it would have taken the internal field, but as we have calculated particularly for inlet and EC, so we are giving this turbulent intensity kinetic energy, which helps us to specify what is the intensity of the K. Okay, so this is done. Now let us go to epsilon. Okay, so this is the epsilon folder. It is a scalar parameter. This is the SI unit of it. So after reading this, you can directly jump to the internal field parameter. So we use it generally for initialization of a particular field. Let us say we have to provide some dummy values to the open form before actually starting to simulate it, because if we are giving 0 here and the value is drastically changing at the inlet patch or the particular patch you are interested, there might be some issue in your solution, and either open form might crash or it will give you some errors. Okay, so then coming to the boundary field, the type of boundary field that we are the type of condition we are imposing here is turbulent mixing length dissipation rate, and we can specify the mixing length as 0.07. uh, it is same for AC and inlet, and for outlet we are keeping it as 0 gradient. Again they have specified AC here, and there is wall, and we generally in until and unless we have the mixing length value, what we generally do is we specify the epsilon wall functions to every patch that we are specifying in your epsilon file value. Okay, so all the files are done, and now we are good to go. If you just open the all run file, so all run file is asking you to clean the foam clean case, then simple foam. Okay, so let me do it. I'll do foam clean case. Okay. So it has is the screen visible?
Yes, please.
So what we can do now, we can go to, let us say, a particular folder. Let us go to case with common, and let us go to velocity folder, and let's just start running it. So it will run, it will take some time, and in the meantime we can continue our presentation till the solver is running. So ART foam, so ART foam stands for, it is the custom code developed in OpenFOAM that calculates the air residence time. It's air residence time in the particular field. Hence, it is given the name ART, and it solves the scalar transport equation for variable S, and it represents how long the air stays in the particular region. So yesterday, on the day one, Ivan sir demonstrated you how you can implement the scalar transport form in your particular open form equation. But what is exactly the scalar transport form? So we will understand about that as well. Before doing that, let me open another terminal. And open form 9. So the foundation version is sourced. Now I'll go to run directory, clear ls, then I'll go to msv. So we are in this folder, and there is a folder called ART form in the readme file as well. Before simulating our case, our aim is to firstly compile our particular solver and then use the ART form. So they have given how you can compile your particular solver. So by going cd in ART form folder and then type wclean and then use wmake command in your terminal. So wclean command is used whenever you have some pre-existing folders or C++ code remaining in your make file. So if something unnecessary is there, the wclean command cleans it, and if I want to compile the new fresh code, I'll compile it using wmake. So for wmake, there are some definitions. I'll just briefly explain you about it. I won't take much of your time. So the artform.c, the description of this solver is, the application name is artform, and the description of this solver is it solves for the air residence time, and that is ART. So it is calling some header files. What are they? So we'll see. First is create time.h. So if you can see here, it is create time.h. What this file is doing is it is defining our simulation time. Then create mesh.h. So it is loading the computational mesh that we are interested in. Then create fields.h. The create fields is the it reads the s, u, and constant parameters. Keep in mind the s is our air residence time, ART. U is our velocity, and if necessary, there are any constant. They are also calculated in this particular file. And then we are implementing a while loop. You can check this. If someone is interested to know more about this, as Ivan sir has said, they can explore the open form programmer's guide and check it themselves. And at the end, uh, it is it is writing all the time steps at the end. And what is the solver's workflow? So what the solver is doing here is it is firstly reading the mesh and the fields that are available. Then we are initializing s and u. So we will firstly run this case called velocity. Then we will compile the solver. As here you can see, the solver is running for velocity. We will now compile the solver, and once this velocity folder is ready and ran properly, we will just take the velocity folder from the velocity folder from the velocity case and place it in the ART case. So here in the readme file, if you can read, they have specifically mentioned about it, what you have to do. So for running ART, air residence case, download the ART folder, save it in your run folder in OpenFOAM, go to the terminal and copy the latest velocity file. So latest velocity file stands for the time being the velocity case has been executed, and paste and replace it with the 0 folder in your ART case. Okay, and by using cd command, go in the ART folder and then type bash all run command in your terminal. And after the successful process, you can visualize the results in the parallel. Okay, so in the meantime, what I'll do is I'll list out what is there. Then I'll go in ART form, and first I'll do wclean, and now I'll do wmake. So wclean is firstly I'll list out what is here. So there is a make folder, there is a artform.c, we have just seen it, and this is createfields.h. So it is a header file. So we defined our different values in this header files, and we are just calling it in artform. So we can now compile it. So to compile any solver, all you have to do is just wmake, and it will start compiling. Have some patience, it will compile, and it will yes, it is okay. So the compilation of the solver is done, and if you want to see how we want to, or as we have compiled our solver, but we really want to check if the solver has been compiled or not, so we can use this command. It is called echo command is generally used for calling out some variables, irrespective of anything. The echo command is just used for calling any variable. So we'll do echo home underscore user underscore admin. So here we can see we are having OpenFOAM queries platform, and here we have our solver. And if you want to see artform is particularly present or not, so we can go in the folder called this variable, and we can find if there is artform or not. So let us do that as well. So yes, so we are able to see that artform is there. The source code is successfully compiled. And now we are ready to move towards the ART foam simulation as well. Okay, so I'll just come back out of it. I'll list out, and the simulation is running for almost now 1800 time steps. So I'll just terminate it and I'll go in the directory. So what they have asked us in the readme file is that go in your 0 folder, open it, and copy the newest velocity file, copy it and paste it in the ART forms 0th folder. If there is, so it is asking the velocity file is already existing. Do you want to replace it or not? So we'll just hit replace. It is replaced. Now what I'll do is one step backwards. Go in ART form, and here again it is doing the same thing. The only difference is here it is calculating the air residence time, and earlier we were solving for pressure and velocity in the velocity case. So I'll just run my all run file, and it has started to solve. So we can wait for some time, or I have a separate folder where I have uh, taken out the results as well. So if you let us see here, and before going to uh, visualization and everything, let us first understand what is scalar transport form. So many of us are from engineering background, and many of us might have been gone through the Reynolds experiment, that helps us to identify the Reynolds number in a particular pipe. So what it does is, what we are doing is, we are just injecting the dye in this pipe to check the nature of fluid. This dye is not impacting the flow parameters. We are just expecting how it will. We are just importing a scalar, and we are trying to see how the internal fluid is going to behave. It is exactly the same. Only thing is we are going to implement it in the form of air residence in open form. So the only difference here is we are injecting dye in this experiment, and in open form we are customly writing source codes for it and visualizing it. Okay, so so this case has been the case I have ran here. So we have stopped the simulation at 1800, but I have ran it for almost 5000 iterations. So we'll start visualizing it one by one, and in the meantime I'll zoom out the screen so that it will be better for you to visualize as well. Zoom, just yeah, okay. So I'll copy the address, and I'll stop this simulating it as we have already simulated it. Rather than wasting RAM on different solvers, let us just wait. So as you can see here, out of 16, 13.4 GBs of RAM has already been captured. So we'll go one by one and try to visualize the contours that we are expecting. Oh, we have not made any phone.phone file. So here we are just making a foam.foam folder. So the foam.foam folder has been created. So let us go, and we will learn about some basic post-processing methods in Paraview as well. So just hang on for a minute. Okay, so this is the simulation. We turn on the visible data scale range. So here, if you are able to see, there are two exhausts. One is here and another one is here. The AC is placed 2 meter upwards from the wall. And once I visualize velocity, you will be also able to see the door that is acting as a fluid type inlet. So I visualize velocity. So see here, we are able to see the door, the AC, the exhaust, and the dual exhaust. Okay. So now you have extracted this paraview file, but now you want to post process it. And as this is a steady state data, we have not incorporated the transient case or density driven flow. So you will not get any temperature values here. Our only aim was to check are single exhaust better or dual exhaust. So for that, what we can do is we can plot some uh, planes. We can take some planes at let us say y normal. You can see here the y is in this case, so we are taking it in y normal, and let us plot it at 1.6. So 1.6 is very downward, so let's do it 2. Okay, 2 is okay, and in the x direction it is 2.3, so I'll reduce it to 2 as well. And you can manually change it also if you want to see it like this, or if you want to play with this filter, you can play with it. For the timing, I'll hit apply. So I have extracted this, but we are not able to see anything because of the pressure that is here. Now once I switch to velocity, you might be able to see this is the AC, but okay, I understand this might be tough. Let me do one thing. I'll reduce the opacity to 0.25 so that you are able to see the velocity here as well, the exhaust portions, and the fluid velocity that is coming from the inlet. Now here, if you are able to see, our plane is just slightly above the door, so we are not able to see the velocity that is coming due to fluid from this direction as well. So we'll just change the direction of the plane to a little bit. Okay, we can position it in the direction of exhaust. So here we can see the fluid velocity is coming from the from fluid type inlet, and the velocity is also coming from the AC, and it is being captured by the exhaust placed in the back wall. And once we take plane upwards, it will be also captured by this exhaust. Okay, so this is one type of uh, post processing. Let us say you want to change uh, the way we view, or you want to change the color. So what you can do is you can go on slice 1, and in that you can edit this, edit under coloring section. So there are multiple maps, so I generally prefer rainbow uniform. So now you might be able to see it in a very different way. Let me increase the legend for you, and and we will do it. We will not keep this as velocity. So this is our velocity of AC coming through. This is the velocity of our fluid inlet that is coming, and these are the velocity for the exhaust valve that we have added here and here. So we can again, if you want, on you have to be very careful while plotting or while switching from one place to another, because what generally happens is you are trying to implement something on form.form file, but it will occur on slice one. Okay, let's say I want to plot glyphs. So if I hit glyph, I want orientation array of view, and I don't want scale array. So I'll turn it off and hit 2.5, and the total number of let us say 1000. Okay, so if I hit enter apply, so here I'll be able to see some recirculation zone. But as this filter is already been applied, let us do one thing. Let us change it into solid color, and here we are seeing the pressure parameter, change it to velocity. Okay, so we will be able to see a small recirculation zone that is occurring here. So it is and we can see here as well, the velocity is, it is turning little bit. Also, what you can do is you have plotted the glyph, but you want the glyph on form.form. So rather than again selecting form.form, again plotting the glyph, what you can do is just hit the glyph, right click it, and go to the change input parameter, and here we can see the select input. It is asking to select me a particular input. So right now, to plot the streamlines, we are using slice, but I want the velocity vectors on the form.form file. I'll hit OK. So now the velocity vectors are throughout the whole domain. Okay, I'll turn this off. They are too much clumsy and I just don't know what is happening. So what I can do is I can again go here, and I'll take a plane vertical to this direction. I'll hit apply. So now I won't be able to see anything. Just a minute. As here again see uh, this the slice, the source of this slice is, if we see, the source of this slice is glyphs. So we are plotting slice on the glyph, which is not expected. We want slice on the form.form file. So once I hit OK, so now yes, so it is now working. Okay, so in the negative x direction, I'll click on the slice, I'll turn it off, and select the velocity parameter. Again, you won't be able to understand what is happening. So I'll turn on the form.form file and view it in the 3D parameter. And on this slice, I'll try to plot my glyphs. So we are just trying to visualize how the velocity is working in this whole domain, and how you can post process your data. Okay, so let us go to orientation array. U is okay. We don't want any scale array. Just a minute, and I want it as 0.25 and 1000. Hit apply. Okay, so these are the pressure contours, but as we are not interested in pressure as of now, you can turn them to velocity and you can visualize it as well. -6. So here you are clearly able to see the recirculation zone. If not, let me change the color. I'll just change it to solid color. Okay, so in the 3D case, if you are able to see in the near exhaust, we are also able to see a recirculation zone, and that is really important for us to find out that are there any particular dead zones or recirculation zones that are occurring. So there are basically two recirculation zones, as we can see. First is coming due to the AC's inlet velocity, and the second is coming due to the door that is acting as the fluid inlet velocity. So there are two recirculation zone in this domain. Okay, let me turn this off, and the form.form file, let us keep it acting. So let us say you want to capture this snapshot of this. So what you can do is, first you want to write something here. So you go on sources and on annotation. Okay, in annotation you can write your 3D text, or you can just basically add your text. So let us say we will write as simulation of ventilation at, so the time step here is at 500 seconds. 500 seconds. Okay, so I have applied this, but I want it to be bold. So there are some things you can keep this in the center as well. You can do one thing, you can change the font. These are the same fonts that we generally use in our Word file or presentation file. So let us keep it Arial only. Let us change it to 30. So it has increased. We can increase it to 35 as well. And once this is done, we can select the color scheme, that if I want the text in red, it will be displayed in red. But for the time being, let us keep this in black. And if you want to play around these settings, how much parameters do you want? If you want this text to be bold, you can do it. So now this text will be seen in bold. You can bold this particular text. So let us do times 40. Okay. uh, in some simulation, the people generally do not require for this XY orientation, so we can turn this off as well by using this filter. So here you can see, if I click it, your XY plane or the 3D plane will be gone. And again, if you want to see the orientation axis, you can hit it. Okay. And again, so here your text is visible, but if you are carrying out a simulation, you have written 5000 seconds here, but how you can prove it? So rather than proving, how you can show it? So again, in annotation, you can go annotate time. Okay, and you have to keep everything as it is. You have to just add, this is basically an advantage. What you can do is just you can add s at the end. So once this is done, you will be able to see the time is 5000 seconds at the end. So let us say if I write seconds, so 5000 seconds will be also seen, but second doesn't feel really good. So we just go with capital S. Okay, and generally we keep it in the bottom. So we are, I mean, the text is written in the upward part, and the font is written, the time is written in the downward part. I generally follow this way. You can change it as well. So let us say you are using this particular font with, let us say 40. The font size is 40, and you want it bold, or you want it italic, or you want the shadow of this text. So there are multiple post processing things that you can do with this. Okay. Also, I would like to show you one filter. So this is, you can use control plus spacebar, and here you can go to plot data. Okay, plot data, you have to hit enter and apply. Okay, so here it is um, very ill distributed. So what you can do is, um, here I'll just maximize it. So it will show what it has listed out. So it has listed velocity magnitude, epsilon values, internal k values. So I don't want this, so this will be gone. All I want is the u magnitude. I'll just select this, and I'll close the left axis custom range and bottom axis custom range as well. And I'll just take this. So you can simulate your velocity as well. And if you want to export this, you can plot your velocity as well. If you want to export this into a CSV data, or you want to check these values in your Excel sheet, be careful that you are in this particular window, because what happens is, if you are here, a blue border line will be created if that tells you in which particular window you are working. As we want data from this end, you can select this. A blue line will be created. These are generally beginners level mistakes only, so I am highlighting them because generally, even when I was learning OpenFOAM, I faced similar mistakes. So what you can do is, if you are on this field, just go here, and there is an option to save data. So it will save it as the file. Let us do demo. Okay, and you're good to go. And here there are choose arrays to write. So I'll select it and I'll deselect. So all I want is velocity. So I'll just use velocity and hit OK. So it will be saved. I can visualize it later. Okay. First, I'll just tell you how you can do various types of post processing. So again, by clicking this, rather if you are not comfortable using some hotkeys on keyboard, rather than selecting Control plus spacebar, what you can do is you can go in filters. So there are some tabs. If you are using a particular filter very recently, it will show you that what filters you are working on. And if you want to see all the filters that are available, so just go to the alphabetical part. Just a minute. uh, yes, uh, on the form.form file, just go to the alphabetical part. Here you will be able to see all the types of filters that are existing on the ribbon as well. So you will be seeing the filters that are available on this ribbon. So let us say if you want to extract a contour, or you want to clip this domain, or if you want to take this slice, this will be available. Moreover, some more filters will be also more filters can be also seen. Okay, so let us say you do plot data over time. I'm quite sure keep it will take too much time, and this paraview also will crash due to RAM limitation. So what we can do is we can use the plot data over line, and here uh, just a minute, I'll turn off the second slice and turn on the first slice. Okay, it is bit show plane. I take it bit upwards, so that it is okay. So it has plotted a data particular on the time. I don't want that, and I'll go in plot data over line, change the input, and I want on my slice one. So the plot data on line one will come into play. So here are some settings that you can change. Plot data over line. You can say show line. So if you want to see the line, you can see it. And let us keep the orientation axis also as of now. And let us try to capture some data. Okay. So you can manually move it. Let us say I'm keeping it here and here. So you can see in 2D view, you won't be able to capture it fully. Okay, let us say you have placed your filter like this, but in the 2D view, let us say like this. But once you turn your filter to 3D, again there will be some issues that you are dealing with. Okay, so please take care of that as well before doing. So this is what I was saying in 2D view. Let us switch to 3D and just plot a simple basic data overline. Okay. I'll so it is saying that it is showing, but I am unable to see. In that case, what you can do is you can just there is a filter here, render view. So either you can view it in the side or you can view it in the bottom. So and go in the quartile chart. So if you enter it, and you can basically see all of your parameters that are there in this folder. Wait. Uh, Let us do render view. And, spreadsheet view. Okay, I can tell about this as well. So I want to visualize. So what it has done is it has captured all the cell values that are there. Arc length represents the distance of your plot data over line, and it has captured every value. Okay, we can go till the bottom and we can see the arc length, that is almost around 6.32 meters. And as of now it is showing the the velocity, or there is nothing. So let us change it as well. uh, Change the input source to form file. Okay, again spreadsheet again. And I want plot data overlay. Okay, so as you are able to see the data here, again what you can do is basically you can play around with these filters and test it out for yourself as well. And let us say you have done a particular simulation, okay, and you want to save it, uh, like you want to save as it is, because once you will open the paraview, you have to do everything from the scratch. So what you can do there as well, okay, you will go in file and you will go in the save state. Okay, once you save state, there is a paraview state file called .pvsn. It will be saved. So let us do demo.pvsn, and this paraview file is saved. Now whenever you open it, let me do it. So pvsn file has been uh, saved, and it is asking me how to open. So I'll do it with paraview here. Yeah, so if you are able to see, it will load everything. See, it has opened everything from scratch. All I have done is went into the file and saved the state. Okay, so this was about basic post processing in Paraview. Let us now see how we can plot the air residence as well. So I'll do just delete downstream filter. Okay, yes, and I'll go in the velocity folder. So we have just copied the velocity folder from ART form, from velocity to this ART form. It has carried out 600 simulation right now. So let us see and try to visualize and see if there is some change. So as you can see, the air residence is occurring. The only thing is we are particularly taking it for some values. Okay, it is still developing. You have to run it for, let's say, almost 2000 seconds or 2000 iterations, then it will show you some quite good results. So this is the velocity plot and this is the air residence plot. What you can do is, again, you can take a slice here in the y normal at 1.6 and hit apply, and you will be able to see the air residence as well and how it is behaving in the room. You can check the values from this end, and if you want to change the color scheme, just go in the style editing and select a color map from default. So let us go in rainbow uniform, and from the rainbow uniform you'll be able to see how the time residence is working. Okay, so it is still developing. It is around 350, you may say. Yeah, so it is almost around 350. And by this, you can, by varying the time step data, you can check for particular time step, how much value do you want. Okay, so just let me go to my presentation real quick. We have compiled the solver, we have checked. So this data is from the report, and they have just did the same. We have plotted streamlines and they have found out recirculation zone near AC and recirculation zone near exhaust. and we have also simulated the recirculation zone here. So we were able to capture the streamline accurately. And once this time residence plot for exhaust, once your simulation is fully developed, what you can do is you can go in the again you can take slices and plot at variable values of height. Uh, and in the results and discussion, a small recirculation zone is formed at the top corner of the room besides the AC. Thank you. And this was all from my end. Also, if you can see the case study, this case study was more about machine learning and development of machine learning uh, models for predicting the accurate position of your AC, how accurately you want to place your AC. So this tutorial was more related to that. What you can do is, personally, I haven't checked machine learning for OpenFOAM, but if you are new to it and you want to explore, there are some two files that are given. You can open them individually as well and check for yourself that how they are, what model they are using, what data set they are using, and how they are training data, which model they are implementing, and how much loss is occurring in the machine learning function, and how they are again reincorporating the absolute error. Okay, so this is for 1.3. You can check it out for 1.6 as well. The data set is given here, and in the report you can in deep you can learn about how to implement machine learning models. Also, I have, as I said, how the Reynolds number came out to be different for so Reynolds number 1 has been considered for calculation. So you can check it out for yourself. They have detailedly explained how they have predicted it. If you can see, this is machine learning data. The red line represents the predicted data, and the blue line predicts the actual data. So it is quite accurate. I won't say quite. I mean, it is nearly around 90% accurate. But if you want to deep dive into machine learning using these solvers, you can do them. Okay. So I'll come on the chat box for now. Let us take some chats as we have some time. Uh, can I show the presentation that I have made in the morning for calculation of 5 plus? If you guys are okay, then we can do that as well. Or okay, please. Okay. So you guys are comfortable, right? Okay. So, okay. Manjil sir has answered some questions as well. Okay, which case? Okay, Ajit sir, what you can do is, is my screen visible? Can anyone just type yes?
Yes, Paris.
Okay, Ivan sir. So what you can do is, Mr. Ajit sir, you can go on the CFD FOSSEE home website, and in the home, you will be able to navigate to the case study project. In the case study, here you will see the completed case study. In that, just scroll down and go to the case study number 150. Okay, so this is study of airflow and impact of exhaust on window AC and split AC on air ventilation. There are various machine learning models implemented as well. So here you can see this is an approach of CFD with machine learning. So you can check it out. See, improving air quality in classroom using ART form and machine learning to expedite simulation results. So you can check it for yourself as well, and you can try it out. Okay, as we have let's say 20 minutes, I would just like to complete my previous simulation presentation that we were discussing about. Just give me some time. And also just a minute, there is a filter called stream tracer. So Mr. Ivan Fernandez and Mr. John sir, from the FOSI IIT Bombay team were working on the post processing of this particular case. So they have come up with the particle tracking to test out how a particular parameter of velocity works out. So you can see here, I have taken some plots as well. I'll open it with VLC. So here you can see this is the indoor inlet, indoor that is working as inlet. This is working as the AC, and there are two exhaust. So you can see the velocity particle that once the flow develops, how it is going, and it will hit the wall now, and it will change its direction. So you can see it has changed the direction. In this case, we haven't done ray tracing because my system would crash as it is very RAM consuming. But there are various cases as well. Mr. Ivan sir has captured it very nicely. You can see. So here the velocity behaves in different way. So you can try it out for your particular range of interest. You can specify it in ray tracing and check how the air is behaving in your domain. Okay, so let us go to SnappyXmesh PPT. And yeah, I mean, if you want to run your simulation in parallel, so the one command that you are expected to use is lscpu. Just a minute. Yes, so I'll go here, and now I'll go 2412. Okay, so what I'll do is I'll do now lscpu. Let us do lscpu. So ls is just nothing but just list out your CPU details. So it has clearly mentioned what are threads per core, what are cores per socket, and how much socket do you have. So here, if you want to calculate the physical cores, so physical cores is given by number of cores per socket into number of socket. Okay, so if you can see, number of cores per socket is 8, and the number of socket that I have, my particular system, is 1. So physical cores that I have are 8 cores, and these are actual cores and processing units in the CPU, and it can execute instructions that we give at a time. Okay, and if I want to find out the total number of cores, so there is different formula, that is number of physical cores that we have calculated in the equation 1 into number of cores, number of threads per core. So here the number of threads per core is 2. So our case for my system, it will become 8 into 2, that is 16 cores. If you are uncomfortable with this, it is still okay. What you can do is you can go in your task manager, performance, and in CPU. Here you can logically check how much logical processors are there, total number of cores are your processors, and how many cores are there. Okay, and see the socket value is also same. And here is your GPU stats. So I have a dedicated GPU memory of 4 GBs only. Okay, so this information is helpful when you are running your simulation in parallel. Okay, if you are running your simulation in serial, there is no use of this, but you should know how you can calculate this. So these were commands that we used in the morning session. Okay, so we will just briefly go with y plus and why it is used. So here you can see there is an airfoil, and here the flow separation is occurring, and you can change the angle of impact for this particular airfoil, and you can calculate the flow separation that is occurring at the trailing edge of the airfoil. So why is y plus important? Let us understand what is y plus first. So y plus is a non-dimensional wall distance used to evaluate the mesh near the wall in turbulent flows. So in turbulent flow, there is too much chaos occurring. So to accurately capture what is exactly happening in this region, we generally model the Y plus. Okay, and this is the importance of it, that it ensures correct boundary layer resolution. Y plus is very helpful in modeling our turbulence as well, and it also helps us to choose the wall treatment approach. So this is, let us say, this is our wall, and flow is the free stream velocity is coming from this end, you can see. So here the eddies are forming, and there are three layers. So one is buffer layer, the second is log law region, and this is the outer layer, and this is the edge of the boundary, and ahead it we can see the free stream velocity. So what generally happens is, this is large LES stands for large eddy simulation. So whenever your cell count is very, 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 very small, we generally tend to keep the Y plus value around 1, where we want to fully resolve the viscous sublayer. Viscous sublayer is this region. We want to accurately capture even a single eddy. Means minute of the minute eddy. When we want to capture the minute of the minute eddy, we aim for the Y plus value of 1. And if we are using any turbulence model like K epsilon or K omega that we saw in the previous heat transfer case study, so we can target any Y plus value of 30 to 300. And even Nikhil sir in today's morning session, he was also talking about the Y plus value, where his Y plus value was around 150. Okay, so you can find various Y plus calculators as well. But if you want to manually calculate your Y plus value, there is a particular way to do that, provided you do some assumptions. First thing, the working fluid that we are considering here is air at 15 degree. The density of air is 1.225 kg per meter cube, and the dynamic viscosity of this fluid is 1.8 into 10 to the power 5 kg per meter second. Uh, Here, the main assumption is the free stream velocity that we are expecting. As the free stream velocity will change, your Y plus value will also change. Okay, so just keep in mind, keep to fix your to calculate Y plus, first you have to fix your free stream velocity value. Okay, so as usual, first thing first, we will calculate the Reynolds number is given by density into your free stream velocity into your characteristic length. Here in our case, as we were working on a flow over a cylinder, the diameter of this case was 0.1 meter. So we are using 0.1 here as well. And the dynamic viscosity that comes out to be 34,027, which falls under the category of turbulent flow. And then the coefficient of friction, CF value. So there are two CF values you can calculate. You can calculate one CF value for external aerodynamics, and there are different CF values for internal flows. Let's say you are modeling flow inside a pipe, so the CF value that I'm using here will change. Okay, just find out your CF value and your majority work will be done. Okay, so this is the constant number that we are using, and Reynolds number we are using from equation 1. So 0.058 into Reynolds number to the power minus 0.2. So this came out to be 0.000719. Okay, so we have our CF value as well with us. So we have our Reynolds number, we have our CF value. Now we will be calculating the shear stress. So tau W, it is denoted by tau W. You can calculate it by writing 1 by 2 into your CF value into density into free stream velocity square. So 1 by 2 can be written in form as decimal as 0.5. The CF value can be written as 0.000719 that we have calculated here from 2, CF value from 2. The density that we have assumed here is 1.225 kg per meter cube, and as we have assumed the velocity that we are going to provide our cylinder will be 5 meter per second. So the square of 5 stands for 25, so we have used 25 here. Okay, so the shear stress value came out to be 0.011 kg per meter second square. After calculating the shear stress, you will go to the velocity shear that is occurring. It is nothing but the under root of the shear stress divided by the density. That came out to be 0.0947 meter per second square. And here we have specified that shear stress we have taken from equation 3. Okay, so we have now our velocity shear. And now first cell thickness y. So in snappy x mesh, if you see, there is a line where you can specify your first cell thickness. Okay, so as we were targeting the y plus value of 1, I have taken it as 1. We are fully resolving the viscous sublayer into dynamic viscosity, into this velocity shear, and into density. So we are expecting 1 here, y plus value. So our first cell thickness comes out to be near around 0.000155 meter, or 155 mm. But in, as you know, in open form, we cannot specify values in terms of mm, so you have to give it in terms of meter. So you can directly write this value in your first cell thickness in snappy x mesh. I'll show that as well. Okay, and these are the commands that were used to run your meshing in serial or parallel. The only thing extra we are doing here is decompose power and running the particular solver in parallel. What you can do is you can just replace it. Let us say you want to solve anything. Let us say you want to solve simple form. So you have to just replace it. You have to use decompose power. Only thing changes here is MPR run, and the number of processors will be 10, and the application name will be simple form, and we will be running in parallel. And again, it is up to you. If you want to reconstruct this mesh, you can, uh, but in paraview there is a filter called decomposed case, so you can view it in decomposed situation as well. And there was one thing that I wanted to tell you. Let us say you are making any mesh in ANSYS, and if you want to import it into OpenFOAM, how you can do that? So I have some case with me. I'll try to show you. Mm, So this was a folder I was working in my undergraduate days. I was working on a duct simulation. So in that time, while doing my meshing, I made this mesh on ANSYS Fluent, but I wanted it to export it into OpenFOAM. So you have to do nothing. Just go in the system folder. There will be a foam data to Fluent. If you don't know how to find it, as I mentioned, you can go to your tutorials folder. I need to open source my bash script. Okay, now you'll go to the examples, and again using the grep command -r, I want to search this fluent data to foam. Let us in, I want to find it in foam underscore. Let us wait for some time. It has jumbled up something. Wait, what we can do is fluent okay. So here there is a file called fluent mesh to foam. So you have to do nothing but just go and copy this. It is located in incompressible icofoam folder in the elbow case. You can just copy it and it is here in our case, what I'm trying to convert is the ventilation vent mesh, and here they are trying to convert the elbow mesh. Okay, so I'll do nothing. I'll go here again, and okay, so we are here, and there is the file called fluent data to foam as well. So you have to do nothing. You have to just run fluent mesh to foam, and you have to write the name of the file that you want to convert it into open form readable format. So in my case, it is meshvent.msh. The .msh represents the fluent extension. Okay, so just write meshvent.msh. Okay, so see, it has completed, and it is writing it to the constant polymesh folder, and the execution is done. We can check it as well. For that, we need to make a foam.foam file. Okay, and now we can visualize it. Okay, I'll delete this. Yes. Okay, so this was the vent. My fluid was coming from this end, and it was getting separated at these channels. So this was only done to check if meshing is working or not. So yes, it is working. This mesh was created in ANSYS, and now we have imported it to OpenFOAM. The only thing we need to take care about of this is while we are developing the mesh in ANSYS, at that time only you have to specify the name selections. In ANSYS, you have the name selection parameters where you have to specify the names of your particular region. So let us say I named it inlet or outlet. So if that is done, you won't be facing any issue converting your fluent mesh to foam. Okay, and also I have some plots on when I was working on a heat ventilation cooling case. uh, I came out with some files, so you can have a look at this as well. So this is the U magnitude and T temperature, how they are varying with respect to time in your region. Let us say volumetric 2D. So the the chilled air was coming from this end. Using the duct, it went here, and then the aim was to cool this room. So using this post processing techniques, I've done that, and nearly around you can say 2300 seconds, the room started cooling completely. This is the velocity plot, how the velocity will look like once you render it. This is this is the comparison plot of how your temperature is gradually changing with respect to time. Once the room becomes cool, it will achieve a steady state and a straight line. You can see here. And let me check if I have something. So this was the final video that I demonstrated. This was the 3D view. So the flow was coming from this end, and we captured it in the whole room. And I wanted to see how the flow regimes are working. I took a clip in uh, in this direction so that I could see how the cooling is happening in the particular region. This is the top view. top 2D view where you can, simulate or see how it is getting cooled from the top. And this is the temperature value. I have plotted data over time. It is a time consuming filter, but it will work eventually. And once the room is getting cooled, the simulation is also reaching the steady state. Also, I have plotted the residual.
1 second, we have just posted the attendance of
Yes,
the
ma'am.
second half today. So
Sure,
please
ma'am.
pause for 1 minute and then mark themselves present. So participants, please mark this as present. We have just given the link for the attendance. And
Sure.
I'm also pasting the Zoom link for yesterday's session. So every day we will be, posting, we will be saving the Zoom recordings in this particular link that I have pasted. Like for today's recordings, tomorrow also you will get the recordings in the same link that I have shared now. And it's recommended that you download it because maybe within 3-4 weeks, this link will no more exist. So if you're done with the attendance, we can continue.
Yes, ma'am. I'm also done. Just 5 more minutes.
Yeah, okay.
Also in Paraview is very good post-processing tool. You can select a particular contour and check how it is moving. So in my case, the room was heated at 310 Kelvin, and I wanted to see how the room would look like for the 290 K contour. So you can see as the time progresses, the 290 is cold air will start occupying the room, and there was just an outlet that was provided the air to go. And it has started capturing the room. See, as we have had our session on ventilation and flow around the buildings. So in my undergraduate days, I was also working on plume dispersion on some flow analysis. So I have done some flow analysis as well. I have I have these plots, so I'll just show them to you. So you can have an idea how you can post process your data in OpenFOAM. So this was the building. This is a tutorial case. I haven't developed this from my own. There is a tutorial called flow over buildings. You can find it and you can replicate this as well. So this was the velocity plot. This was the mesh. I've taken a slice uh, along the buildings to check how fine the mesh was. And I have also done some simulation on flow over cylinder. So you can plot your Strawhall number as well. So it was comparison. Let me show you. See, once the flow is being developed, the once the frequency starts, you will be able to see the means it will start capturing the frequency as well. This was a transient simulation, and it means I did this simulation when I was just learning OpenFOAM. I was not very not very uh, good at it. I was just learning OpenFOAM. So yeah, that's all from my end. It is almost. I hope you guys have enjoyed it. If you have any questions, we can have a chat. And as I can see, Ivan sir, Pranay sir, and Manjil sir have already answered many of the questions. So yeah, thank you and Yeah, okay. Can you please tell about location in mesh? Okay, very nice point. Okay, just Pile ma'am, can we have 2 minutes, 2 or 3 minutes more? I'll just wind it up if it is
Yes, yes.
okay. Okay, so when I was learning open form, okay, my screen is not visible now. Just a minute. Is the screen visible?
Yes, please.
Okay. So what you can do is you can go in the, let us say, lowers and in the form file. So there was an error due to location in mesh, and I was not able to rectify what was the issue. So what I did was, okay, this is different case. Sorry. Over cylinder mesh form, and yeah. So yes, so there was a particular error I was continuously facing. The location is very ill defined. The entry is very primitive and it is very wrongly defined. So I was not able to figure out what was happening until and unless what happened is, this is the form, and when we specify our location in mesh, uh, if it is working, I'll just show you system and snappiness. So what I was doing is I was directly giving the values as 0.5, 0.5, and according to the uh, geometry. So I was facing an error. The error was because the point that I was expecting inside my geometry, it was coinciding with the nodes that were here. So what a good approach or a steady approach is, what you can do is, again, you can go in filters, search, and you can go to point. So this is a filter called point source. You can hit enter. So your point has been visualized. Okay. And just copy this coordinates and paste them here. Okay. 0.001, 0.001, and it was 0.053. Okay, hit apply, but you won't be able to see it very nicely, so just change the color of it so that use some dark color so that you will be, and here you can see we are not conflicting with any region inside the mesh. Okay, so sometimes what happens is the point in your mesh will exactly coincide with the domain that you have here. So this is a very good approach. You can randomly move this point as well, but it is a very good approach to, just check by plotting the point source and check that if this point is not conflicting and not causing any issues. Yeah, that was it. Yes. Okay. Case study website into Windows and copy to WSL OpenFOAM and run step by step with commands. I'm facing some issues. Okay, sir. Also, I mean, we have sessions scheduled for tomorrow as well. So, if your error is not resolved at that point, we can do something after it. Okay. We can demonstrate it. No problem. We can go step by step as well. It is 5:10 already, and I just want to thank everyone who are present here. You guys have been a very really nice audience. Listen to me, and I hope if you have any questions, you can just directly ask Payal ma'am. She can get back to us, or you can ask it tomorrow as well. Okay. So
I think one more question was there, right? And the last.
okay. Big thanks.
No, right? No, it was taken.
Okay. Thank you, Mohit. Thank you. It means a lot. Yes, I mean, Payal ma'am, all the questions are done. Yes, yes,
Okay. In that case, we can wind up for today.
yes.
Or should we wait for maybe 30
Okay,
seconds or another 1 minute and then we can wind up?
okay, okay.
So tomorrow in the morning half, we'll have the session by Dr. Joseph Prabhu. So all of you please join around 10:25 or so, so that we can begin at 10:30. Yes, buddies. So everybody is thanking you. It was actually a very good session, very detailed one.
Actually, I'm really humbled to get your responses. Thank to Payal ma'am as well. Thank you, ma'am.
Okay, I think we can wind up the session for the day. Thank you so much everybody for joining. Thank you for being patient, and thanks for all the appreciation. Thanks. Bye bye.
Have a nice day ahead. Thank you.
Yeah. Have a nice day. Bye bye.